Good morning. We will give it a couple of minutes for other people to join, and then we'll get started. Good morning. So, good morning to all. I think we can get started since the people trickling in, or the flow of people trickling in, is more or less stagnating. So, okay, let's slowly get started. All right. So, welcome to Scientific C++, and I'll start by sharing my screen. Okay, the interface seems to have slightly changed, but no problem. Okay. Yes. All right. So I'm going to switch to the chat view so that I can see that. And let's start with this. So basically, this is the web page for this particular training, and it contains some information about the learning goals on the one hand, the learning outcomes, about tentative schedule, which probably we won't keep properly, but whatever. And also, and this is probably the most interesting part, there is also a link to a GitHub repository. In that GitHub repository, you will find a number of things. Let's switch to it. So basically, you will find there the slides which I'm using. So you can simply download those. You will also find, and that's more interesting perhaps, a link to the source code. Basically, that means that any example that is in the slides also exists as a C++ file, so that you can actually look at it in more detail if you want to, because of course screen real estate is precious, so I can't fit everything on the screen, and hence sometimes you'd be better off to look at the original source code. So you can find that in this directory. I'll post the link to this page in the chat, and I'll do that probably a few more times, because if you join the session late, then you don't get to see this. Okay, so that's a useful resource. Feel free to either clone the repository, fork the repository, whatever. It is public, so everyone has access to this material. If you were to reuse it, there is a license. So basically, it's free to use, but you have to attribute it to the original creator, which is me. So that's the only restriction I impose. Okay, so let me switch to the slides. And I'll also do quite some stuff hands-on. So I'll switch back and forth between a terminal and this slide deck. But for now, let's start with the slides. A few practical things. So if there are any questions at any point, please feel free to type them in the chat. We're not awfully many, so basically if you prefer to ask your question, then you can also activate your microphone. That's no problem. If you type a question in the chat, I'll either deal with it immediately because I try to keep an eye on the chat at all times. But I might also postpone the response to a more appropriate moment during the training. So that's one practical thing. Please ask questions. The more interactive this is, the more pleasant it is for me, and perhaps the more useful it is for you. So use the opportunity to ask questions if you like. Okay, another practical thing. I'm recording these sessions. The recordings will not be made public, but they will be available to you if you ask. So I put them on YouTube, but as unlisted videos. So I can send you the link if you would like to review this particular training. So for today and tomorrow, we have the same link for Collaborate. So that's not a problem. For next week, it's a different link. It's already in the mail which I sent you, so you should have that information already. I have to switch links because I can make a session repeat, but not in that particular pattern. So that's basically why there are two links. Other things, yeah, so just to avoid all confusion, this is a training that is composed of 4 parts. So today is the first, tomorrow is the second part, next week will be the third and the fourth part. So it's not a repetition, it is really each time a continuation of this particular training. All right, so this is a link to the repository I already mentioned, so you already have the link in the chat. This is a link to our VSC LinkedIn page. Feel free to follow us. There's usually interesting news about HPC, about evolutions in the Flemish Supercomputing Center, about trainings, about new things which happen there. So feel free to follow us. All right, let's start with a small introduction and perhaps motivation of why you would want to be here. You'll probably all have your reasons, but maybe it's good to comment a little bit on why I think knowing C++ is a good idea. One of the things is, of course, it's an industrial strength programming language. What I mean by that is that it's a very good language if you want an application that has good performance. Then it's quite a good programming language. It's also a very good programming language because it allows you to create large-scale systems, software systems. So basically, it's a language that is designed for large applications. That's also very useful. So it's also a good long-term investment since C++ has been popular for years and is still quite popular. It's usually in the top 3 languages which are most used or most in demand. So it's, in my opinion, good investment of your time to get acquainted with C++, to learn how to use it efficiently. It's of course it's a general purpose language. It is used for many things, ranging from system programming to scientific programming, to creation of applications with graphical user interfaces and whatnot. So it is very versatile, and it can be used for many purposes, which makes it, in my opinion, again, an interesting language to use. It is quite feature rich in the sense that you can mix and match various paradigms. It's of course an imperative language, such as C++, such as MATLAB, but it's also object-oriented. And it also has functional features, so you can do functional style programming in C++, which is a bonus since you can just pick the style which best fits your particular need at some particular point in the project. So that's, in my opinion, also a very good thing. It comes with a large standard library, which typically is of high quality. So that again is quite a bonus since you get many data structures. We will see a couple of examples of that, and other features in a way for free without having to install extra libraries and so on. And of course, it has already mentioned excellent performance. Well, when you know what you're doing, that's a caveat. You can write extremely slow C++ programs. That's not so very hard to do, but if you know what you're doing, you get really, really good performance. The drawback of C++, though, is that it is not that easy. I'd argue that that is in part due to historical reasons. Basically, C++ started out back in the 80s, and it has evolved over time. And it's still backward compatible with these early versions, and that makes it a very large language. So there are a lot of features which are kind of duplicated in some ways. And sometimes there are very good reasons for that. For instance, if you deal with arrays in C++ or with sequences of data, there are many ways to do that. And all have their strengths and weaknesses. So there it's a very good thing that there is choice. In other cases, it is just due to the fact that it's backward compatibility, and then it might not be such a good idea. So what I will try to do is to talk about modern C++ and skip over all the old style features, which are not really recommended for production use anymore. So basically, I'll also use some quotes from time to time, and they typically intend to make a point. And this particular one is by Björn Strastrup, and that is actually the creator of C++. So his name will pop up quite a number of times during this training. Okay, so basically you could learn other languages as well. For instance, if you're really hardcore into scientific programming, you might want to learn Fortran. It's a very good idea. Fortran is a modern programming language which has many interesting features for scientific computing. So go ahead and learn it. It's a very good idea. Also, Python, of course, is a very good candidate, but a combination of Python and C++, in my opinion, is a very good idea, because then you can leverage the strengths of both languages, you can leverage the performance of C++, and the ease of use for prototyping, for scaffolding software, which you can do easily with Python. So that makes for a very powerful combination. This is not the topic of this particular training. If you're interested in that kind of things, there is a training about Python for HPC, which explicitly deals with that kind of considerations. Okay, so the scope of this particular training, there are some prerequisites. You are supposed to be fluent in another programming language, basically whatever that is. So this is not a training to teach you how to program. If you don't know how to program, this will be very hard, because it's fairly fast-paced in the sense that, for instance, repetition statements, okay, I mention them, and I'm supposing that you know them from other languages. So I concentrate on differences rather than the particulars, well, the general meaning of an iteration statement, for instance. So basically, there are also a number of limitations because you can create training of a week, an entire week, about C++. That's definitely not a problem. So I limit myself to a subset of C++, which is most useful for scientific computing. So I will talk at length about data structures, which are useful, about numerics, and about data processing. So of course that comes at some cost because you can't deal with everything. And I'll mention that, what I leave out, what is further to be explored, and so on. I'll mention throughout the training. But the goal is mainly to give you, let's say, a subset of C++, to deal with a subset of C++ that's, in my opinion, is most useful for scientific computing, because that's what I'm supposing you're here for. You're scientists, you want to do scientific computing. Okay. And this is again a quote by Bjarne Stroustrup. And I also lean heavily on a book he's written. It's on the next slide. But basically, this quote again goes back to what I mentioned, that in fact C++ is a very large language. It has many features, but there is a core of it which is actually important and which is actually what you should use. And this again is what I'm concentrating on. So a little bit of history. C++ was created, as I mentioned, by Bjarne Stroustrup, and it goes back to the 80s. There have been many changes over the years. The first standard which was published as an ISO standard was in 1998. And I'd call that the coming of age of C++ because that was the first standardization effort. There was a C++ 03, which corrected the C++ 98 standard, but yeah, that's not so very interesting. But in 2011, things got very interesting because over the years, with experience, people realized that there were some very good ideas in the C++ 98 specification, but also some things which were somewhat suboptimal. And hence, C++ 11 tried to deal with that, made a lot of things a lot easier to do. And from that time on, we get a new specification or an updated specification every 3 years. And you see the pattern here. We had one in 2011, in 2014, in 2017, 2020. We'll have a new one this year in 23 and so on. So basically, typically, the C++ 2014 fixed things in 2011. While C++ 17 introduced quite some new features. C++ 20 is a bit of a mix. Some stuff that was introduced in 2017 was improved upon, was fixed when it was not really a good idea. And it also introduced quite some new features, and that again we'll see in 2023. So if you look at documentation or you look at examples of C++, be a little bit careful about which version of C++ it is. Because if you use features which were introduced in the more recent standards, then you might find yourself in a bit of a problem because not all compilers support those. So it's possible that you develop your code and things work, and then you publish your code, someone wants to compile it with a different compiler, and it fails because certain features which you use and which are indeed in the C++ whatever standard are not supported by the compiler or not supported entirely by the compiler. So that's something to keep in mind. So I'll stick mostly to C++ 17 in this training with a few features of C++ 20 thrown in. I'll steer clear of C++ 23 because it's really too early to use that in production, in my opinion. Okay, so that gives you a bit of a historical overview. We will also talk, well, a little bit, I'd say quite a bit, about the STL. So that's the standard template library, and that's the standard library which I mentioned. So this is also definitely a subject of this training, and I'll talk about some of its features, not all of its features, because yeah, it's way too extensive to cover completely. But we'll cover a good part, and again, I'll try to cover the part which seems most relevant for scientific computing. All right. So the presentation and also the whole concept of the training is based on a book, A Tour of C++ by Björn Strastrup. And the most recent edition is the third one, which was published in September 2022. You will find a reference to that book at the end of the slide deck. There is a list of references, and this book obviously is mentioned. Okay, a few typographical conventions throughout the slides. So if there is a shell command, for instance, this command to compile a C++ program, I'll use this kind of layout. So basically it will be on a black background, and I'll use a prompt here, this $, in order to indicate that this is a command line thing. And of course, don't type the $. I mean, it's just to note that this is a command line prompt. So inline code fragments will be rendered in this, well, somewhat ugly font to make them stand out from the running text. And longer code fragments will be in the same font, but on a grayish background. Data files will be on a yellowish background, or greenish, whatever that color is. So basically that it's clear from the layout, from the formatting, that this is data and not code. What you will see, unfortunately, it's quite often, is this ellipsis here. And that just means that some stuff is not shown, that I don't have the screen real estate to show all the code or all the data. But again, don't worry, because either these parts of the code will be dealt with on the next slide or have been dealt with on a previous slide, or you can find it in its entirety, the whole source code, in the GitHub repository. Okay, so before we get started, I'd like to get a little bit of terminology out of the way, because it's something I use a lot, and it's important that we're on the same page about what that means. So syntax versus semantics. Syntax has to do with form, it's the grammar. And essentially syntax is easy, because if you have a syntactic error, the compiler is going to tell you. It's going to say, hey, look, what you've written here, I can't interpret this, and I think the problem with that is the following. Please correct. That's basically the idea about syntax. And to make it more clear, I'll give you an example from natural language, because we're all familiar, of course, with natural language, and we know perfectly well what syntax is there. So, for instance, in English, the phrase "the dog is barking" is correct. It's syntactically correct. The dog is the subject is the subject of the sentence. The barking is okay with respect to the is, and the is in the right tense in order to match the subject, and so on and so on. So perfectly fine. On the other hand, the dog barking is clearly incorrect. So the syntax is wrong because the verb is actually missing. So this is syntax. It's easy. Also, for instance, if you use Word, Word is going to tell you, well, up to a point, about syntactic errors. Okay, so that's all easy. What is more difficult is semantics, because that has to do with meaning, and that means interpretation. That, of course, is a much more fuzzy subject. Again, let me give you an example of natural language. So the dog barked would be correct, both syntactically, but also semantically, because that's what dogs do. That's the sound they make. They bark. Easy. Okay. On the other hand, the dog spoke is syntactically correct. I mean, that sentence is okay, but the meaning is not okay. So semantically, it's not correct because dogs don't speak, unless in fairy tales or something like that. But apart from that, dogs do not speak. So this is wrong. So this already illustrates an important thing. A sentence, or let's return to programming, computer programming can be syntactically correct, but semantically wrong. So it will compile, it will run, it might crash, which means that semantically it's not okay, or it might run, but give you wrong results. So that's semantics, that's not syntax. And that's much harder to spot. Again, syntax, that's just your compiler telling you that it was a bad idea. Semantically, the compiler can help you a little bit, but not very much. So we'll see what the compiler can do in that respect. There's also some additional software that you can use, which will help you a little bit, but mostly semantics is up to you. So that's an important distinction. It's two words which I'll use quite a lot. So it's good to have that out of the way. All right. So this was my introduction. Are there any questions? Meanwhile, I'll put a link, because I saw that someone else joined. I'll put a link to the repository and the slides and so on again in the chat. Are there any questions at this point? So the difference between each modern C++ version? Yeah, okay. No, in the sense, so the question is the difference between, say, C++ 2011 and C++ 2017 as large as the one between Python 2 and Python 3? Yes and no. So no, in the sense that the new versions of C++ don't break anything. So any valid C++ 98 program is still going to be valid C++ 23. No problem. So in that respect, the answer is no. If we look at the number of new features implemented both in the language and in the standard template library, then the answer could be yes. Then you would have quite a difference. For instance, the number of new features in C++ 17 is really quite large. So yeah, there is significant difference, but always backward compatible. And that's of course very nice. And that's also what makes C++ an industrial strength language, in the sense that if you wrote a proper program that adhered to the C++ 1998 standard in 2001, your program is still going to compile and run correctly at this point in time. So that's the good thing. So I think that kind of answers your question. Okay. Is there any? Are there any other questions?
Yeah, I do.
Okay.
So how does C++ relate to C?
Okay. So yeah, it's a good point. Very good question. So basically, we had C. C is a much older language than C++. It dates down to late 60s, and it was standardized in when was it? In 89 was the first ISO standardization, if memory serves, of C. So it's an older language, and it served as inspiration for C++. So C++ inherits quite a lot from C. I'll point that out at some points. So still in modern C++, you sometimes see features which inherited from C. Sometimes that's a good idea. Sometimes it's a very bad idea. And sometimes it's unavoidable. So I'll point that out. But yes, there is a lot of C in C++. For instance, many of the grammatical structures, like iteration statements, if statements, are still the same as they used to be in C, up to C++ 2014. In 2017, the if statement, for instance, was optionally modified. So you have a different form of the if statement, which would definitely not be compatible with C. So you could say that in some sense, C++ is an extension of C. And certainly back in the days when Starstrup created C, that was definitely the case, and that was also his goal. He actually wanted to have object-oriented features for C. That was his design goal of C++. Meanwhile, routes have diverged considerably, let's put it that way. From time to time, I'll also highlight differences between C and C++. This might also be a very good point to ask you a question. Could you please type, or maybe I can do a poll, that's probably a little easier. Let me do briefly a poll. Sorry, I have to create this, and that takes a while. I can't do that in advance, unfortunately, with this. Well, as far as I know, I can't do it in advance. So, which programming language are you most familiar with? Okay, I can't do more than 5, so that will have to do. All right. So if you could answer that poll, why am I asking? Well, basically, I would like to know because I will, on a regular basis, make references to other languages. So if I know which languages are relevant, I can make relevant remarks in that respect to compare programming languages and features. If there are any languages which are not in my poll, which are relevant to you, then just put it in the chat, because I can only give you 5 alternatives. And of course, there are more languages than those. Okay, so it seems that Python and MATLAB are clear winners. And yeah, there is a little bit of C, a little bit of Fortran, and a little bit of R, but mostly Python and MATLAB. Okay, I'll take that into account, and I'll give examples which are relevant to those languages. Excellent. All right, let's get started on, let's say, the basic features of C++. So let me return to the previous slide. So as you can see, for each section, there is the corresponding chapter listed in A Tour of C++ by Starstrup. And this is the first chapter, and it gives a whirlwind tour of C++. So the basic features, nothing spectacular, but just so that we're on the same page about the, let's say, the more basic features of programming languages, in this case C++. What you will also see is a link to the GitHub repository, source directory, where the code fragments which are shown in the slides, are in entire programs which you can actually compile and run. And that's the same for all the sections. I'll always work that particular way. Okay, yes. Okay, so another question in the chat. What is the ideal or the best C++ development environment? Okay, so that depends a little bit. For large projects, I'd say yes, perhaps use an IDE. There are a couple of them which I like. One which I'm rather fond of is CLion. I'll put that in the chat. But that's a commercial product. So I like that environment. It's actually by the same company, and the name at the moment completely escapes me, which makes PyCharm. So those of you who are familiar with PyCharm, CLion might be a good option because it's very similar in design. So I like that one. It's quite nice. Of course, you can also work with VS Code, and that is also a very feasible solution. Absolutely, yes, exactly. JetBrains, thank you. Correct. So VS Code is also definitely an option to do. Personally, I'm very old school. I just use Vim in a terminal, and basically that's my primary development environment. Yes, it has some limitations, but on the other hand, I can work very fast in Vim, and typically, okay, I know VS Code has Vim bindings and so on, but still, I often run into a lack of features with respect to the Vim key bindings and so on. And then, yeah, okay. So also for me, I work a lot on supercomputing infrastructure, and then often it's just easier to work in the terminal than with graphical user interface. So, but that's my personal take on that. Of course, you can also use the community edition of Visual Studio. So not Visual Studio Code, but full-fledged development environment. That's also an option. It's, in my opinion, fairly complex to set up and so on, but yeah, okay, it does the job quite well. So that's definitely another option. You can also turn to Eclipse, which is free, of course. It's also quite good. So yeah, you have quite a number of choices. I think, I'm guessing, that in the references, let me have a look, there should be references to whatever further reading, online learning resources, tools. Yes, so there is something here, but I don't seem to mention IDEs. Yes, and so there is indeed a reference to both CLion and Eclipse. So yeah, it's that's my recommendation. So what I personally use also on my own computer as a development environment, and that's actually pretty nice. Let me go back to the basic section here. So what I use as a development environment, or yeah, okay, that's actually Windows Terminal with WSL. So that is Linux on a Windows machine, and that allows me to do most. Let me resize this so that I can still see the chat. That allows me to do most things which I can do on a Linux machine, and do that just on my laptop, which runs Windows because I need to use PowerPoint and Excel and Word for administrative purposes, and still want something to do some decent development on. So that is in fact rather nice. Also because I can use containers and can have different development environment with different versions of compilers very easily. So that's, to me, quite important, and that's why I like this particular environment. I might show you later on how that works and why I rather like that setup. Okay, let's get started then, unless there are other questions about IDEs or whatever. If not, let's start our brief tour of C++ basic features. Okay, let's go. So, anything you do in programming starts with hello world. You already know that. That is tradition, so I have to do that. And this is a minimal hello world. So any C++ program application has one and exactly one function, which is called main. It has to have it, and it has to have only one. So this is a function. It's the main function, and I'll go into the details in a minute. I'll analyze this step by step. So let's just assume that we know how this works. How do we get it to run? Well, that's quite easy. We have to compile it and we have to link it. Either you do that using an IDE. If you do that on the command line, you can just do G++, for instance, which is one of the C++ compilers which are easy to install on a Linux system. We can specify a number of things. So one thing is the C++ standard which we want to use. I think by default now it uses C++17, so you probably don't need to specify this in general. But if you want to make sure that a certain standard is used, then you can specify this flag. The -w all is quite useful because that will generate warnings. The W is for warnings, and that is always useful. So in general, my advice is if you compile and you get warnings, do something about it. There are two possibilities. Either you don't know what the warnings mean, that's a very bad thing, because they might point to something that essentially is a problem. So there are two options. In that case, look it up. So try to understand what the warning is about and either solve it, make sure that the warning goes away, or if you're sure that the warning can be ignored safely, just leave it as is. But don't leave a warning if you're not sure what it's about. That's very important advice, because otherwise you may have subtle errors in your code and things may go haywire later on, maybe in subtle ways which you don't even notice. Okay, then the -g flag means add debugging information to the executable. There is a lot of confusion about this. People say, okay, my code will run slowly and so on and so on. No, your code will run just as fast. Only your application will be a little bigger. It will take up a little more space on your hard disk because some pointers to the source code are included in the executable. And that makes it easy to debug your code. I'll also show you how to use GDB, so the command line debugger. But of course, if you're using an IDE, then you have a visual debugger built in, which may be a little easier to use. But again, it's a useful skill to be able to use GDB, especially if you're working in an HPC environment where you don't always have the option to have a graphical user interface. Then the last flag is -o, and that just specifies the name of the application, of the executable, which you want to create. And then finally, you list the source code which you want to compile. So the hello CPP is this file over here. Okay, and then you can run the application by simply executing the executable, and you get a result in the terminal. So that's quite straightforward. I'll do that quite a number of times, so I'm not going to demonstrate it right now. Okay, let's dissect this code a little bit, piece by piece, so that we know what we are talking about. Okay, so the first thing you notice in any C++ file, with very few exceptions, is a number of include statements. And in fact, to put things right from the start, this is not really C++. So this #include thing is in fact a preprocessor command. We'll talk about the build process of C++ later on in much more detail, but just remember this is not really C++. What does it do? It makes declarations of functions and data types and whatnot for IO stream available in your source code. Well, available to the compiler. So then the next question is, what is IO stream? Basically, that has to do with input-output. And I'll point out in a minute why we need this in this particular program. Because this is a very short program and already we need to use the standard library. Okay, so the main function, this is a function, and it's just the function with a definition like any other function. So the name of the function is main. That's easy. And the whole thing, this whole first line, is in fact the function signature. And basically, it defines the input argument of the function and the output type of the result, the type of the result of that function. That is the function declaration. And since it also has a body, it is also the definition of a function. So in C++, we make the distinction between a declaration of a function, that's just type of arguments, name of function, and return type, and its definition, which also contains the payload, what the function is doing. So this part here between the curly brackets, opening here, closing there, well, not closing actually, is in fact the body of the function. So this is what will be executed if this function is called, or when this function is called. So that's basically the idea. So as you can see, there is a return statement, and of course, if you're into Python or even into Fortran, you know what the return statement does. It terminates the execution of the function, and it will pass a computed result, which was computed in the function, to the calling context, to wherever that function was called. Now, the return value in this particular case is 0, which seems likely to be an integer, which is good because that's exactly the return type of our main function. So yeah, this matches. 0 is an integer, and we expect integer output from main. So that's quite okay. And that's the exit code of the program. We'll talk about that in a bit more detail later on. Okay. So one thing in C++, which is actually quite interesting, is namespaces. And you can compare that a little bit to if you do in Python, you can do an import of a module. And you can also do an import as. So the import as thing in Python sort of resembles a namespace. Modules sort of resemble namespaces in C++. Not quite. So it's not a one-to-one, but it serves the same purpose. It serves the purpose of avoiding conflicts, naming conflicts. So functions and variables with the same name can exist in multiple namespaces. You also know that from Python. So that's important to realize that they do exist and that they are available. You can create your own namespaces. Namespaces can be nested in C++. We'll talk about them in more detail later. So for instance, the standard library is in the namespace std. So in IOStream, you would have things like cout, endline, etc., and they all live in the namespace std. So either you can prefix with a namespace, so std cout or std endline, or you can do using namespace std, and that makes available all the functions and types and variables and whatnot, which are defined in that namespace into the context of this using statement. And of course, the using statement holds downward. So basically, from the point where it is written, up to the end of the file. So I can use just cout rather than std cout. I can use endline rather than std endline. Okay, personally, I don't consider this good practice, to be honest, and I never do this. I never do using namespace std. However, I'm going to assume that I do this all the time in these slides just to save some space, because each time typing the std double colon just eats up space which I don't have on slides. So basically, if you look at the source code in the repository, you'll see that there is very little usage of this std namespace using namespace std. I hardly ever do that because, again, I don't like it. It's the same thing as in Python doing an from some module import star. This is kind of the same thing. In Python, that's bad practice. Well, I consider it bad practice here as well. But you will see it often in example code, and some people like it. Sometimes I also do it, but very rarely actually, because I have no idea what's in the standard namespace. I mean, that's the entire STL, so what do I know? So I'll get a lot of things there in now my default namespace, which I have no clue about what they are and even that they're there. So bad idea. However, again, I kind of have to do it in the slides because otherwise I don't get any code on my slides and it gets a little tedious. Okay. A question. How does one know that IOStream comes with standard namespace? Because all the STL stuff is in the standard namespace. That's easy. Anything you import from the standard library is there. By the way, how do you know what's in the standard library? Let me switch to hold for a second. This is a very nice site. It's the CPP reference, and this really gives you an overview of whatever is in the STL, and also an overview of features of the language. This, of course, is a reference in the sense that you already need to know some C++ in order to use this effectively. But it's an excellent reference. I'll put it in the chat now. It's, of course, also referenced in the slides at the end. I hope. If not, I'd have to add it, but I think it is. Okay. So one of the things to note, by the way, since we're here anyway, is after each section, you see when it was introduced. So, for instance, variants and any were introduced in C++ 17. I'll talk about variants probably, any maybe. So that's fairly recent. Pair, for instance, and tuple were introduced in C++ 11. But you also see that there is very new stuff, like here a flat multi-map, which is introduced in C++ 23. So it's interesting to have a look what it does, but I would suggest not to use it because most likely compilers are not really going to support it or are not going to support it well yet. So it's better to wait a little bit with those features. But this is an excellent tool, and frankly, I use it all the time. Okay. So again, I will assume using namespace std in the slides. I'll mention std a couple of times, so to make sure that we are still on the same page about it. If I do live coding, I will not use using namespace std. I'll always do the std thing right. Okay, so one of the things that, well, the only thing essentially that the hello world thing is doing is writing stuff to the screen. And this is streaming I/O. So basically, cout is an output device, is an output stream. Let's use the right term. It's an output stream. So I can send stuff to it. And the way to send stuff to it is using this operator. So the less than is one single thing. It's an operator, and it will send the string hello to cout. It will also send argv1, we'll discuss what that is later, also to cout. It will send another string to cout and end line to cout. Okay? So both cout and end line are defined or are declared in IOStream. So if I do include IOStream and I do using namespaces std, I can just use cout end line. Without using namespaces std, I'd have to write std double colon cout, std double colon end line. That's the idea. Okay, what's the end line doing? Well, you may know that depending on which operating system you're using, text files have different line endings. For instance, on Linux and macOS, at least the current macOS, text lines are ended with a single character, which is new line. However, on Windows, text files are ending with two characters, carriage return and new line. So basically, depending on the platform I'm using, I'd have to change my line ending. And that's where end line comes in. So it will automatically issue the right characters to end the line. Carriage return line feed on new line on Windows, just a new line on Linux. So in that respect, it is quite convenient if you're concerned with cross-platform compatibility. However, there are caveats to using endline. It's not necessarily good for performance of I/O. So don't ever use endline in a for loop that does intensive I/O. I'll come back to that later on, and we might even benchmark that a bit. Okay, so basically the strings here and the values are sent to the cout stream, and that's the send to operator. Okay, so this already shows how to have literal strings, so sequences of characters in C++. We enclose them by double quotes. So in Python, you can choose either you delimit a string by single quotes or double quotes. In C++, you don't have a choice, it's double quotes only. So single quotes also exist, but it's something else. We'll see it in a minute. Okay. How do we get things in? Well, we want two, or well, actually three ways to get data into our application. And of course, if you're familiar with Linux, then you know that you can specify command line arguments. And actually, our Hello World program can deal with a command line argument. And it's using that in order to print a specific message. So for instance, if I run hello.exe with world as an argument, I get hello world. If I run it with C++, I get hello C++. Okay, so the arguments are passed into my application at runtime. How does that work? Well, that's actually what the arguments of main are for. And this is an inheritance of C. This is the exact same way that C does this. And this is actually very unfortunate because it also means that we have to use C-style strings in this context, while C++ has much better strings, as we'll see later. But okay, we have to live with it. So there are two things here, two arguments. There's argc and there's argv. Okay, argc is argument count. All right, so that means the number of command line arguments that you pass to your application. Almost, but not quite. Because actually there was one more. The string ./hello.exe will also be available in this array argv. So basically, the first argument the first element of argv is going to be, sorry, ./hello.exe. The second is going to be the string world. Now, arrays in C++ are indexed starting from 0. This is not a surprise for the Python people. It may be a surprise for the MATLAB people, because if you have a vector in MATLAB, the first element is at index 1. If you have an array in Python, or if you have a list in Python, whichever your favorite data type, its first element will always be at index 0. So that's the same in C++. So argument count is going to be the number of arguments passed on the command line plus 1. And basically that means that world, which is our actual argument, is going to be at index 1 in argv, which is an array of strings. This is very loose speaking, but okay. Conceptually, it's an array of strings, of which I take the second element at index 1. Okay, so this is the way to get command line arguments into your application. Let's perhaps do a little bit of live coding here to make the point a bit more clear. So I'm going to write a small application, command line arguments. Let's see. Right? Can you read the code, or should I enlarge it a bit more? If I have to enlarge it a bit more, just put enlarge or something in the chat. Size it okay. All right. So typically my C+ program starts with include IOStream. If I need any input output, then yeah, that's going to be there. Okay, so I've got my main function. It has argc as an argument, which is an integer. It has an array of character pointers. Okay, this is a lot of words. A list of strings, which contains command line arguments. I'm already going to return 0. Okay, and I'm going to iterate over my array argv. So for int e starts at 0, e is less than argc, and I'm going to put the value of vi to standard output. And here I'm not going to bother with st and line. I'm just going to use \n, so a new line character, to terminate my line. All right, so this should be a valid C++ program, and I'm going to compile that. Just to save some typing, I'm not going to use the -o option. In that case, the compiler is just going to create an executable with the name a.out. Okay, this is just a very small example, so I don't really care. I could add the -w all flag, but there are not going to be any warnings in this particular example. So sometimes I'll also just omit it when I'm pretty sure that I've done the right thing. Okay, let's run that application without any arguments. And as you can see, there is still one thing printed, which is, as I already said, just ./a.out. Okay, so indeed, argv0 is going to be .a.out. And in fact, let me modify the code a little bit. I'm going to add some single quotes here. Let's use some later on. Okay, so if you're used to Python, you would just run your script again. This is a compiled language, so if I make a modification to my source code, I have to recompile. So I did that. Now I'm going to rerun my application, and as you see, now I've get goals around the value which I output, just to make that a little more clear. Okay, if I call it with one argument, let's say ABC, you see that now I get 2 lines of output, one, of course, for the name of my command, and the second for the argument I passed. So let's add some more arguments. And as you can see, now I have quite a lot. And notice that if I want to pass an argument with spaces, I just enclose that argument in quotes. I could use, this is bash, I could use single quotes, I can use double quotes, depending on what I want to do. But as you can see, it's quite convenient to deal with command line arguments. Of course, all the command line arguments are available in my C++ main function as strings. So if I want to do something with the value 15 as if it were an integer, or if I want to do something with 495.3 as a floating point value, I have to convert them first to those types. We'll deal with that later on. Okay, so I hope this clarifies a little bit the magic around argc and argv. Of course, the names are arbitrary, so you could use different names for argc and argv, but by convention, they're always named argc and argv. So I'd suggest you don't deviate from that convention. But of course, you can if you really, really want to. You can. Okay. So what's the meaning of character star? So essentially, character star, we have the type character, and that's just a single character. We'll see it in a couple of slides. And character star is in fact the address of a character somewhere in memory. It's a pointer to a memory location. This is, if you're not familiar with C++, this is a little advanced, and we'll deal with it later on, what it means exactly. For now, I'd say just think of argv as an array of strings. That's the semantics of how we use it. It's an inheritance of C, and arrays in C are, well, crappy, to be honest. But we have to, because that's the way that we get arguments into the main function. We don't have a choice there. That's just how C++ defines it, which is, yeah, unfortunate. I hope, but I've never seen any effort to change this for some reason. I don't know why. Maybe it's just too hard to do it. And to retain backward compatibility, I don't know. I would like to discuss this with someone who's really involved in the standard making, but I don't know those people, so can't ask. Okay, so argc is sort of the, so usually argc represents an address, and it's just a file name. So a.out is just a file name. Here it is, a.out, more than a file name. So if I want a different name, I can just compile my application and give it a name. For instance, whatever. That's all. If I don't specify a name, the name of the executable is going to be a.out. If I specify a name, it's going to be whatever I want. That's basically the idea. So you got that. Yeah, okay. This might come from a Python or MATLAB background. So basically, you cannot run your C++ code. That's just a text file. So what you do is, C++ is a compiled language. So the C++ source code is turned into a bunch of machine instructions. And that bunch of machine instructions is an executable. And in this case, it would be a.out, or now also whatever.exe. let me perhaps immediately show you what happens under the hood. So Compiler Explorer is a very nice tool, which I use quite often. And what it does is essentially show you what a compiler does. So on the left side, you see source code. And in this case, it's a very simple function. I don't remember what it does. It deals with an C-style array, and it compiles it into machine code. So this is the actual machine instructions that are generated by the compiler. And this is at times quite useful because it allows you to inspect what the compiler is doing and see whether it does what you hope it does. For instance, I would like to know in this case whether this code is in fact vectorized or not. And looking at machine instructions, I can tell that it's actually vectorized. So that's a very good thing. The nice thing is you can choose different compilers. For instance, I can choose an older version of GCC. As you can see, I can pick very old versions. If I go down, I can go back to GCC 4.8 and stuff like that. So basically, I can go back in time. It also has the Intel compilers, which is nice. Also the one API compilers from Intel, ICX and so on. So basically, this is quite interesting. Zix C++. Okay, this I don't know. I have to check what that is. No idea. Okay, anyway. So this is a very useful tool, and this is just to show you that what happens is that this C++ code gets translated into machine level instructions, and those are in a way your executable. So that's what's happening under the hood. So that's why I get, after compiling, a new file, which is my executable, which I cannot read, by the way. If I go to cut a.out, you see that I get a lot of stuff which doesn't make any sense. Sometimes this is useful though, because you can see some textual information, typically about your system, where it was compiled, with what compiler it was compiled, etc., etc. So that can be interesting to have a look at. But yeah, you can't make anything reasonable of this. Okay. In main, usually used to open a data file. Yeah, yes, because of course what I can pass on the command line is the file name, and then I can open that file name in my application and so on. We'll do that, but we'll do that later because that's a little involved, and we'll deal with that later. Okay, more or less clear what happens. I'll talk about how things get compiled and so on, about the whole build process of a C++ application in quite a lot more detail. That will maybe today, probably tomorrow, but okay. All right, now we know how to get things into our program, well, at least command line arguments. So that's quite easy. And of course, argc and argv get their values based on the invocation of your executable. That's pretty obvious. It's at runtime when the program starts. Okay, so variables in C++, few surprises. That is convention. So basically, if the operating system is actually starting your C or C++ application, it will make sure that the argc and argv values are set appropriately. So that's actually the job of the operating system when it starts such an application. Okay, what's the difference between different versions of G++? Okay. No, not all versions of C++, of G++ follow the same standards. So basically, if you go back in time to, for instance, sorry, I have to click here, to, for instance, GCC 9, so 9.1, 9.2, etc., etc., then that would be C++ 17, but not entirely implemented. If you go even further back, so to GCC 6, you would have only C++ 2014. If you go to very recent versions, then you have probably for GCC 12, you will probably already have quite some C++ 20 features. So basically that is the generation of your compiler determines the C++ specification which it adheres to. If you want to know which feature is implemented by which compiler, there is a list of that somewhere. I think it's even on CPP reference somewhere, but I'd have to look for it. I'd have to look it up, where that is. It might be this actually. Yeah, I think it's this. Let's have a look. Here, for instance. Yeah, that's it, indeed. This is exactly the table I was looking for. So basically here you see certain features listed, which are specific to C++ 20, and then you see which compiler supported, starting from which version. So for instance, let's take an example. Concepts, for instance, which we are not going to deal with, by the way, are supported, well, partly in GCC 6, but more extensively in GCC 10, and of course in 11, 12, etc., etc. While here, for instance, in this particular compilers, which are old, it's the Sun Oracle compiler. I don't know whether it's still around, actually. I don't really think so. Cray compiler, not in that form, I think. So basically, they don't support any C++ 20 features, as you can see. And here, for instance, the Intel compiler, which is typically quite good, also doesn't support everything. For instance, they implemented it in 2021.6, but they removed it again in 21.7 because probably it was too buggy to fix easily. And here, for instance, lambdas in unevaluated contexts are not supported by the Intel compiler. And there are some features for which you need recent versions of the compiler, but mostly here, for instance, you see that immediate functions were sort of supported in GCC 10, but fully supported in GCC 11. And that's for C++ 20. So if we go to C++ 23, you will see a lot more red, as you can see. Quite a number of things are not implemented yet. That's why typically I'd say sort of stay away from them, because if you rely on them, you also assume that everyone who uses your software has access to this version of the compiler, which is not always the case. So stay clear of it. Okay, so turn to the slides. So a variable, it's always useful, especially for C, C++ type of languages, to remember that a variable is in fact just a name for something that resides in memory. That's my take on it, and it's a useful one in this particular context. So variables names, they just are the same as in Python. I don't think there are any differences. So names always start with either a letter or with an underscore, and they can contain digits and so on. Names are case sensitive. Of course, a variable can change its value during run. That's not surprising to anyone. You can assign new values to variables. That's no problem. But, and that is different from Python and MATLAB, it's of course the same in C and in Fortran, but you have to declare variables. That means you have to say that, for instance, the variable argc, that's its name, is going to have an integer value. And that means that you can only assign integers to that variable. You really reserve that memory space to store variables of that particular type. So that's a bit different with respect to Python and MATLAB. You have to declare your variables before you can actually use them. So for instance here, we have a few variable declarations. So we have a variable with name m and type integer, and its initial value is 13. We have a second variable with name n. It's also of type integer, and its initial value is computed on using the value of m. We can, of course, assign to a variable. We can assign a new name, a new value. For instance, we assign m plus n to the value to the variable m, and we can write them to the screen, etc., etc. So that would be the output. So I don't think there are many surprises there, except for the fact that you have to specify the type of the variable before you use it. This syntax might also seem a little bit odd. So this is variable initialization, and using this curly bracket notation is called a universal initialization. You can do something else. You can also write it like this, as I do here. So I could have a variable, say int m is equal to 5. So this syntax also works. It's slightly different from this one. So I would recommend to use the universal initializer. So basically this curly bracket notation. You will see a lot of example code where that's not done, but there are a few subtle errors which you avoid if you use universal initialization. So I consider it good practice, and I recommend always doing so. The only exception for me is in for loops, where I typically use the assignment operator, since it's, well, more common to do it that way. Okay. So this is both declaration and initialization in one particular statement. You don't have to do that. You can declare a variable without initializing it. Sometimes that makes sense. Sometimes it doesn't. The equality sign is the assignment operator. And it's a little trap in C++, which I will point out later on. But normally it's not a big surprise because you have the same assignment operator in Python and in MATLAB and so on. But there is something a bit tricky about it. I'll show you later. Okay, let's talk a little bit about types. So someone asked, what is char star? Okay, let's forget about the star for a second, but char is a character, so an individual character. And as you can see, a literal value of a character is enclosed in single quotes. So single quotes are for characters, double quotes are for strings in C++, and they're different things. So single quote A is not the same as double quote A. Single quote A is a char, double quote A is a string. So, and that's the difference. Of course, as in Python, there are characters which are denoted by multiple individual symbols. So for instance, \n, it's one character, it's a new line character, but it's written with two symbols. Well, with two characters, but then we get into semantic, into muddy semantics. Okay. So if you want to represent strings in C++, the best way to do it is to use std_string. And that's just a character sequence, for instance, hello, which contains 5 characters, HELLO, and it's in double quotes. You can have the empty string, which is, well, double quote followed by double quote. You can't have an empty character. So that's something that doesn't make any sense, by the way. Okay, so there are integers, and integers are fairly straightforward. It's just to represent integer values. Anything that's countable can be represented by integers. Something that's important to realize when you come from a Python background, in Python, integers don't have an upper limit. You can just keep on adding to integers. They keep on growing until you exhaust the memory of your computer, no problem. That's not the case for integers in C++. In C++, integers typically are represented using 4 bytes. So 4 bytes is 32 bits, which basically means that you have 2 to the power 32 possible integer values. That's it. So that means that the largest integer which you can represent is 2 to the power 31 minus 1. The smallest one is minus 2 to the power 31. So that's your integer range. There are also long integers. I'll talk about them later, and those are represented using 8 bytes or 64 bits. And of course, you can represent much larger integers using those. Okay, this is scientific computing, so we're highly interested in floating point numbers. And again, there are 2 types. So there is float, and that is single precision. So single precision means that you have 7 significant digits, and the smallest non-zero one is 10 to the power minus 38. The largest is 10 to the power 38. And a floating point value uses a 4-byte representation. So again, the Python people don't get confused. A float in Python is double precision. So a float in C and C++ is single precision. Okay, so there is a question about the string type. So a char star is in fact the address of a character. And if you use that to point to a string, to represent a string, then a string is represented as a sequence of characters, so an array of characters, which is terminated by a special character \0, so a null character. That's the way how C represents strings. Okay, so since a string in character array form is always delimited or ended by a null character, you can determine the length of a string because you just have to count the number of non-null characters. If you reach a null character, that's the end of it. So that's sort of reasonable. But there are limitations. One limitation is that you can happily go over the end of a string and have all kind of a character array and have all kind of buffer overflow problems and so on. So an STD string is a more solid type and it has more machinery which you can apply to it. So it's much easier to work with STD string than it is to work with character arrays. Character arrays are an inheritance from C, and of course they are used under the hood by STD string, but it's much more convenient to use C++ own string representation, which is the STD string, rather than its bare bones inheritance from C. So that's more or less the idea there. How to declare an unsigned integer? Okay, so we will come back to integer types in much more detail later on, but the simple answer is just use uint. So I'll put that in the chat. That's an unsigned integer. Sorry, wait. No, that's not an unsigned integer in this format, and it's written wrong, by the way. So that's stupid. So if you want, then it's just unsigned int. So that would work. But there are different types. Like for instance, you have a uint, a 32p type. So that would also be an unsigned integer, 32 bits. So that's another option. So you have actually many integer types. but I'll come back to it later on. So this is just the basics, just to get things done in some examples. Okay, so float is single precision, double is, guess what? Yeah, right, you got it, double precision. So rather than 4 bytes, we use 8 bytes to represent our floating point value, and that gives us 15 digits of precision. So the smallest non-zero value which you can represent is 10 to the power minus 308, and the range is minus 10 to the power 308 to 10 to the power 308. Why do I use different notations for the negative and the positive thing? Okay, that's weird, but okay. It's correct, but it's weird. Anyway, floating point values are represented as you would this is interesting. Yeah, this is actually not correct, what I'm doing here. Because it's fun, it's the first time I see it, or where I notice it. So basically what I've written here are not floating point values. These are double values. Haha, interesting mistake. I have to correct that. So I should add an F here after each value, and if I intend double precision, I don't need to add anything. So if I just write something like 3.5 in C++, that's a double precision value. If I intend it to be a single precision value, I have to add an F. Okay, subtle mistake, which escaped my notice up to this point. I have to correct it. Okay, let me take a note, because there are already 2 things which I want to change. If I now can find some paper, that would also be convenient. There is, of course, lots of paper here, but I'm not sure I can use it to write. Yes, I can't write on. Okay, this I can write on. All right. So types, I need to correct a few things. Float values, because that's bad. And also notation. Okay. All right. Does that mean that the number minus? Yes, it's double. Exactly. Yeah. So the compiler will interpret that as a double precision number, and typically it doesn't matter, because if you assign it to a float, it will be converted. But that is the problem. It will be converted. So if you do that often, you lose performance. So it also means that if you use floating point values, you multiply them by a constant which is double, the whole computation will be done in double precision, while you intend it to be done in single precision. So that's a performance thing. The semantics is okay, that's no problem, but the performance is bad, or is worse than you might expect. But we'll return to this. Well, this is something I typically mention in a training on code optimization, but probably it's also somewhere when we talk in more detail about types, because this is just a brief introduction, but there is more to come about that. Okay. So one of the things you also have, and again, it's not a surprise to Python people, you have the type bool, and that of course has 2 values, true and false. Note they don't start with capital T and capital F in C++, it's just lowercase. Okay, so operations and math functions. So for integer, float, and double, we have addition, subtraction, multiplication, division. But one thing to remember, if you divide 2 integers, you get integer division. So that's like Python 2. Python 3 changed that. That was one of the more nasty changes which they made from Python 2 to Python 3. But C++, just like Fortran, just like Python 2 in the old days, is going to return 0 if you divide the integer 3 by the integer 5. So for integers, you get integer division. So that's important to remember, because it's often the cause of subtle bugs, because you think, okay, 3 divided by 5 is going to be, okay, I don't know, what is it, 0 dot something something something, yeah, 0 .6. But no, it's not, it's going to be 0. For integer, you also have the percentage operator, which is the modulo operator. Not really surprising to most, I think. Then you have Boolean operators. So you have the logical AND, that's a double ampersand. The logical OR, that's a double pipe. And the logical NOT, which is just an exclamation mark. Note that there's also another operator, which is a single ampersand, and another operator, which is a single pipe. Those are bitwise operations, so don't confuse them. The logical operators are double ampersand, double pipe. Okay, comparison. So for characters, for strings, for integers, and so on, you can test for equality. So that's double equality. For difference, that's exclamation mark equality, and then the usual less than or equal, etc., etc. For float and for double, of course, we have the same operators, the same comparison operators, but it rarely makes sense to test for equality for float or double values. Why? Because they're typically subject to round-off errors, and the probability that you will get mathematically equal values, well, that you get equal floating point values for where you would expect it mathematically, is actually, well, pretty, your probability is pretty low. Okay, is this clear to everyone? Because this is important in scientific computing. If you're really into scientific computing, you know this, but to compare strings, you just, if you compare strings, you just see whether they have the same sequence of characters. Very simple. And lower than, and okay, probably the question is more about less than and so on. So that's a lexical comparison. So basically it is according to ASCII values. So that means, for instance, that let's say the string uppercase A is less than the string lowercase a, because the ASCII value of an uppercase A is 65, while the ASCII value of a lowercase a is 97. So the comparison in that case is on ASCII value, so you get lexical comparison, not alphabetic comparison. And that was probably what you were asking about. Okay, but do I need to point out why I have trouble with comparing equality for floating and doubles? Is this clear to everyone why this is problematic? Because this is important that you understand this if you're into scientific computing. I would assume you already know, but if not, please tell me, then I just give you an example. Okay, you all know. Excellent. All right. So basically, what I typically do to compare rounded values, yes, of course, you could round the value, or you could say, well, okay, I'm going to compute the difference, take the absolute value and compare that to something. Look whether it's smaller than something or whatever. So that would definitely make sense. I would have to check whether in the CMAT a function has been added to do this, because you have such a function in the math module of Python. I always forget what it's called. I always have to look it up in the documentation. It's something like almost, or something like that, and that allows you to compare numbers based on either a relative or an absolute is close. Yes, that's it, exactly. So that allows you to compare numbers based on either a relative or an absolute difference. So that's very convenient. I'd have to check whether it's in CMOUNT now. I don't know. It would be very convenient. Okay. So basically, here's an example. If you divide 1 by 3, floating point numbers, then you get something. But what do you get? I mean, that's subject to binary representation of a number that is you can't represent by a binary number with 32 or 64 bits, whatever. So basically, that is why this is not necessarily equal, although it mathematically is. Okay. So if you want mathematical functions, just include CMOUNT, and then you get sine, cosine, exponential function, square root, and friends. And perhaps also a function to check whether numbers are close. If I want to know that, I just go to CPP reference. There is a mod thing somewhere, common mod functions. And let's see whether it's there. That does not sound very promising. Basic operations, so probably not. And exponential functions. No, I don't think it's there. But as you can see, there are quite a number of interesting functions. Here's some rounding stuff which you could use. This is interesting. Nearby int. Okay. That's cool. Okay. And that's old, so I should have known it, but probably I forgot about it again. Okay. Floating point manipulation friends. This can also be useful, this next after and stuff, but not really a comparison thing. Okay, maybe in the special functions. What's in the special functions? Because that's new. Oh, yeah. Okay. Special functions. Oh god, elliptic integrals and so on. So that's indeed your special functions. Recognize Legendre functions, Laguerre functions, and so on. So spherical harmonics, etc., etc. So that is just your mathematical special functions. But it's interesting that they are in the C++ standard anyway. Okay, but your basic stuff is in CMOD. All right. So something that you see very often in C++, and Python people are familiar with some of it, is syntactic sugar. So in Fortran or in MATLAB, you would always write something like x is equal to x plus y. In Python and in C++, you can abbreviate this to x plus equals y. So this triple thing here just means it's equivalent. So that has nothing to do with C++. That is just notation, my notation, to indicate that two statements are equivalent. And basically, this is a more convenient way because it saves typing. Now, of course, for this particular example, if my variable names are just one character, I'm not going to save a lot of typing. But of course, if I use proper variable names which are long, then of course this really saves some typing. And you can do that for all the operators. Here's an example for subtraction, for multiplication, and so on. So you can do that for many operators. You can even go a step further. That's something that you can't do in Python. So if I do n is n plus 1, so I increment n by 1, I can indicate that with n plus plus. Okay, can do the same thing for subtraction. There are actually two forms of this. You have the post increment, and that's what's written here. So that basically means first use the value and then increment. So let's have a look. We start with m equal to 3. Okay, that's easy. N is equal to 5. That's also pretty easy. Then I'm going to update the value of m. I'm going to add whatever is here to it. So to do that, I first have to compute n++. All right. So the value which I'm going to use to add to m is the current value of n. So that would be 5. And then I'm going to increment n by 1. So that means that the result will be that m is set to 8 and that n will be 6. And that's exactly what you get out. You have a different form of this, and that is the pre-increment and decrement. So basically almost the same thing, only you prepend the operator to the variable. So now the semantics is different. Now we are first going to update the value of n and use that to add to m. So basically n will be 6 again because it's just incremented by 1. That doesn't change. But the value which is used in this computation is the new value of n, so the incremented one. So that means that m will not be 8, but it will be 9 because I add 6 to it rather than 5 with the post increment. So that's a subtle difference, and that's something that is important to know. Should you rely on this? I would say no, unless you know what you're doing. Just make your code a little more of a buzz if you're not really confident in what this is doing. Should you understand what it does? Yes, because seasoned C++ programmers will really use this extensively. And they will really rely on the difference between post-increment and pre-increments to get things done. So it's important that you know what it does. It's usually not important that you use it. You will start using it over time anyway. Can I omit curly brackets when defining integer? No. So basically, yes, you could write integer m is equal to 3. Yes, this will work. And yes, there is a slight difference. So the difference, I'll give you an example later on, but the difference essentially is that if you use the assignment operator, some type conversions are done silently. And that may sometimes lead to subtle errors. So you catch more unintended behavior if you use the universal initialization with the curly brackets. So that's why in C++ I consider it good practice to use the universal initialization, so the curly bracket stuff, rather than the assignment operator. There are some subtle things which may go wrong if you use the assignment operator and you're not aware of it. The root cause is some automatic conversions which are done in assignment and which are not done in universal initialization. You can also only use universal initialization in initialization, never in assignment. Okay, so it's a subtle thing, but it's good practice to immediately start using that because it can save you some trouble down the road. Okay, so some general remarks about C++. C++ is case sensitive. Yeah, that's for the Fortran people. That pertains to language keywords, but also to variables, functions, class names, etc., etc. So everything in C++ is case sensitive. That's absolutely not a surprise to Python programmers, to MATLAB programmers. It may come as a surprise to Fortran programmers, which is absolutely not case sensitive. Okay, all statements end with a semicolon. That's the law. And that's different from MATLAB, for instance, where adding a semicolon just suppresses output to the screen. Similar for Python. So basically, in C++, we always end statements with a semicolon. That's what the grammar says. Okay, commenting can be done in two ways. You can have inline comments. I should also change this to inline comments rather than line comments. Probably better to use that term. This I have to look up whether I should use inline comment or line comments. Basically, it means from the / onward, this is a comment. So to the end of the line. So the double slash in Python means integer division. In C++, it just means this is a comment. Okay. You also have block comments, so to comment out multiple lines, and this you do by opening with slash star and closing with star slash. Quite easy. So all the lines which are here are comments. So that's just for the compiler, so it knows it. The compiler will ignore that. So it's just for you. Okay. Let's have a break because actually we're a little bit over time with respect to breaks at least. It's not that we are behind, but I should have given you a break earlier. So let's break, and let's break until let's put that on the screen. So let's break until 11. That seems reasonable. So I'll go to fetch some fresh coffee. If there are any questions, meanwhile, feel free to put them in the chat. I'll be back soonish, so probably I'll already deal with them, or otherwise I'll deal with them after the break, depending on the nature of the question and so on. But feel free to put questions in the chat. And see you in 10 minutes. All right. So basically, there is a question about style of comments. You often see line comments used like you do in the first line of the fragment of code which you posted. That's really often done. I don't think it's frowned upon. Typically, you even see people who use multiple line comments after one another. So line after line of double slash, you also see that as well. Personally, I find it a little heavy on the eye, but yeah, okay, it doesn't really matter that much. So I would say for a single line, even if it just contains a comment like in the first line of your code fragment, for me it's perfectly fine. I don't have any problems with it. Certainly not. Okay. I'll post the link to the repository once more in the chat because I noticed that a few people joined after I did that the last time. So it's nothing new, it's just again the link to the repository. Okay, let me share my screen again. Why did I change that? Okay. All right, so there we go. And let's continue. So basically, let's do a little task. Let's say we are set a task, and that task is to transform a data file. And the data file is just a simple text file. It consists of rows and columns, if you want. So basically, each row represents a point. And the first value represents an x coordinate. The second value represents a y coordinate. So you can view this as a two-column file, or you can just view that as a point in a two-dimensional space on each line. Doesn't matter how you view it. That's the format. Okay. And now what we want to do is we want to compute the distance from the origin of such a point. That's of course pretty easy. What we need to do is to square the x and the y coordinates, add them together, and compute the square root. Very easy. And then we write that to a file out.txt. Okay. So what we should end up with is a file out.txt, which you see there. Just remembered that I need to change another thing, which is file name in hello world. Okay. All right. Then, so what are we going to do? How are we going to do this? Well, we need to know a number of things. How do we read data? We already know how to write data. That's easy. SDC out, simple. But how do we read data? So that's one thing we need to know. We will also need some repetition statements because there are multiple lines. So we will need to somehow deal with that. And of course, we will need a function to compute the distance. Computing the distance, I already mentioned it. You just square the x and y coordinates, and that's it. So this is our function. And of course, it's not really surprising. The name of the function is dist. It's easy. And the signature of the function determines the number, the names, and the types of the arguments of that function, of the function parameters. So in this case, double would be the type, x would be the name. And notice that we have to specify the type for each argument. So although x and y are both double precision floating point numbers, we need to specify double twice, once for x, once for y. So that's just the syntax, that's just what C++ asks us to do or expects us to do. Okay, and then we also need to specify the return type of our function, and in this case it's also double precision floating point. It's a double. Okay, so the body of our function is doing our computation. We are using the square root function, so we need to include CMod. Okay, if we do that, we can just use square root. We don't have to do something like std double colon square root. No, if you include CMod, the functions which are declared there are just imported directly into your default namespace. That's just to make your life a little easier, because otherwise you would have to either each time include the std double colon prefix for each time you invoke mathematical function, or you would have to import them explicitly with the using namespaces statement, which would also require quite some typing. So in a way, CMod is a bit of an exception. It's part of the standard library, but no, it defines things in the default namespace. Okay, so I have a variable d, which is of type double. I assign a value to it with the universal initializer, and then I return d. Of course, in practice, if I would do this for keeps, but not to really declare this variable, I would immediately return the square root of x times x plus y times y. So for MATLAB and Python people, it's a little annoying, but no, there is no power operator. So you can't write something like x caret 2 like you would do in MATLAB, or x double star 2 like you would do in Python. There is a power function, but for, let's say, something, I'm sorry, I'm switching to the chat so that I can see if something gets typed. For simple power operations like a square or a cube, you would write x times x rather than power of x and 2. Anyway, so this is our function. Nothing special here, actually. It's just a standard function. Okay, so the function signature is the declaration. So that is the name, the type, and names of the arguments, and the return type. The definition is the declaration plus the implementation, so the statements in the body. So this would be the function body enclosed in curly brackets, as you can see, and all the statements here, in this case 2, are part of that function body, so they will be executed when you call the function. Okay, so no surprises. And of course we have a return value. So in MATLAB you would do this differently, but this is what you would normally also do in Python. Okay, so x, y, and d are local to the function. So the scope of these variables is simply the function itself. If there is an x somewhere else in your code, okay, it has nothing to do with the x which is here. This one has its scope, everything up to the end of the curly brackets. We'll talk a little bit more about scope in a minute. So calling a function is fairly trivial. For instance, here we call the function list with 2 arguments, floating point values, 3.0 and 4.0. Okay, we can of course also pass variables to functions, and then the right thing happens. I mean, there are no surprises here. What happens, of course, is that if you call a function, the values you call it with are assigned to the arguments of your function. So in the function, x will have the value 3.0 upon the first invocation, y will have 4.0 in the first invocation. In the second invocation, of course, x will have the value minus 11.8, and y will have the value 7.23. Normally, this doesn't come as a surprise. Okay. So, function arguments are, of course, assigned when you call the function. That's obvious. And this is exactly similar as what happens in mathematical functions. So there are very little surprises there. So one of the things you might wonder is this called by value or called by reference? And of course, the Fortran people are used to call by reference. The Python people are typically uncertain what is going on, whether it's called by reference or called by value, unless you know quite well in Python what you're doing. So let's have an example. We have our main program, and that's somewhere here between the ellipses. So in the main program, we assign some value to n, and we compute the result of the function factorial with n as an argument. And then we output n at the end of the day. Okay, our function definition is here. So it takes an integer as an argument. The name of that argument is n, and it returns an integer. So we define a local variable result. We assign 1 to it. And while n is larger than or equal to 2, we are going to multiply result by n, and we're going to decrement n by 1. Note that I have an explicit decrement here. I would write this more compact normally, but okay, just for the sake of the argument and to make things not overly complicated, because I want to make a different point, I'm using a very basic syntax here. Okay, and then I return result. So in my function, int n is modified, n is decremented, and its final value by construction is, of course, going to be 1 or 0 if it was called with 0. But certainly it will be less than 2, that's for sure. So now the question is, I can compute the factorial. For factorial 5, the result would be 120, so that would be printed. But if I subsequently print n, what is going to be printed? Is it going to be 5 or 1? So if n is passed by value, then it would be 1. Then it would be 5, sorry. If n is passed by reference, it would be 1. So question is, what does C++ do? The answer is, in C++ we have call by value. So although the only thing which is passed to the function factorial is its value, so not its memory location, which would happen if it were called by reference. So basically, that means that in a way, the argument of the function, if you use call by value, is copied. Of course, that's entirely innocent if you pass a floating point value or an integer or a very simple type to a function, then it doesn't matter. But if you have something more sophisticated, like a vector or something like that, then you have to be very careful, because call by value means that you're going to copy your data structure, which may be quite expensive. So, yeah. C++ offers you an alternative, and that alternative is call by reference. So this is another example where we have the function swap, and if you look at the function swap, it's just going to exchange the values in x and y. Let me perhaps again do some live coding here to show you more visually what's going on. So let me do the swap thing. Make some modifications. All right, so I'll include IOStream, your IOStream 0. In this case, I don't want any command line arguments, so I'm just going to omit them, which I can. Main can have either 0 or 2 arguments. And in this case, I don't want to mess with command line arguments, so I'm just going to not deal with the command line arguments at all. Okay, so my function is swap, all right, and I'm going to swap two integers. So in x and y, Okay, this function is not going to return anything, but I need to specify a return type. In this case, I use void. That just means my function is not going to return anything. So that would be equivalent to a subroutine in Fortran. It would also be equivalent to a Python function that doesn't explicitly return anything, although a Python function actually returns the last thing it computes. So you don't have the equivalent of a void function in Python. Not really. Semantically, yes, but in practice, no. Okay, so I want to swap. So I need a temporary variable, and I assign the value of x to it. To x I assign y, to y I assign emp. Okay, that's it, that's my function. Now, in my main program, I declare two variables, int a 3, and 5b. Let's just for good measure output them. So a is equal to a, b is equal to b, and new line. Okay. Resize this a bit. Yeah, it doesn't. Yeah, I can, but it won't help much. Let me maybe try and decrease the font size just a bit. This is probably, you can probably still read this, yes? Okay. So now let's call swap on A and B and also output it again. Okay. Let's compile this. Nothing happened. Okay. So this did not work as intended. Why? Well, actually, we already know. We have call by value. So basically, what happens? Let me make a small drawing to make that clear. That means that I have to get attach and so on my tablet. That's where I normally use a whiteboard if this were a face-to-face training. Now I need to fuss with tablets and so on. Okay, blah blah blah. Yes, I'm very happy that it respects my privacy. That's really wonderful. Okay, so let's resize this. No, 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 no. Just bloody resize it without trying to force me to do silly things. Come on. Yeah. Okay, got it. Right, so let's, yeah, I can probably remove this, and then I want some pen. Okay. No, I don't want more options. I'm quite happy as it is with this pen, I think. Okay, so what I've got is the memory of my computer, and that's here somewhere. So this is the RAM of my computer. Okay, this is my main program. Okay, I've got A, and I'm going to assign 3 to it. I've got B, and I'm going to assign 5 to it. Okay. Yeah, there's an int here. and there's an int here, and there is more stuff for main, but okay, whatever. So what is going to happen? Well, as I mentioned earlier, in fact, A is just a name for a memory location. So I'll get a location in memory somewhere, and that's going to contain 3. Okay, so this guy here is just a name for that memory location here. Same for me. Different location, different name. This is 5, and this guy is pointing here. Okay, now I've got my function, which is void swap int x int y, and I've got my TMP, so int, and I'm going to use an abbreviation. I'm just going to use T because, okay, I initialize it to x, I assign y to x and t to y. Okay, that's it. And in the main function, I'm going to call swap. So here we have swap AB. Okay, so what is going to happen? When I call this function, okay, I've got x and y, and those will be memory locations. So x is going to point to a new memory location, and in that memory location, I'm going to write 3. Similar for y, there will be 5. So x points to a memory location and a points to a memory location, but those are different memory locations. So now there's also going to be a t somewhere, and in the t I write 3, then I replace 3 by 5 to the memory location that x points to, and 5 by 3 in the memory location that y points to. Okay, now my function is done. All right, all these memory locations go out of scope. Well, the variables go out of scope, so the memory locations are no longer available. Yep, they go away. And in my main program, A still points to 3, to a memory location that contains 3, and B to one that contains 5. Nothing happened. Well, yes, quite something happened under the hood, but with no visible effect in the main program. Okay, so that's, in this case, not what we want. So, how can we deal with this? Well, we can actually indicate that what we pass into our function swap are not values, but references. And that's indicated by the ampersand, which you see after the int type of both arguments. And that means that rather than pointing to a new memory location, x will point to the same memory location as A if I add this ampersand, and y will point to the same memory location as B if I add that ampersand. So now we don't have call by value, now we have call by reference. So if I now call swap, then what happens is, okay, we get our new t, blah, 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 it will contain 3, blah, blah, blah. The 3 will be replaced by 5. The 5 will be replaced by whatever is in t, which is 3. All these references will go away at the end of our function, no problem. But A points to a memory location that contains 5, B points to a memory location that contains 3, which is exactly what I intended. So this is call by reference. So just like in Fortran, you can choose between call by value and call by reference. Also in C++, you can do that. So passing by reference allows you to change the variables you pass into the function in the calling context. And it also avoids copying. So you typically use references for two purposes, either because you really want to change the value of a variable in the function, or because you want to avoid a copy, which is expensive in terms of compute time and memory. So that's basically the idea. So you have a choice. We will come back to that in much more detail later on. So this is really a reference to an integer. And that's what the ampersand indicates. Okay.
Can I ask a question here, maybe?
Go ahead.
So we now still basically had to swap in memory the values of A and
Yes.
B. And I suppose there's also a way to do this even more efficiently by swapping just the pointer of A and B itself.
The internal A and B. This I don't quite get.
So instead of swapping in memory the values, 3 and 5, swap around where A points and where B points.
You can do that, but then you would really have to work with addresses. Then you would have to work with pointer variables. That's something you can do. That's something that we will also discuss. But in this case, I'd consider it a little bit overkill. I would consider it overkill for small numbers, for small types, like integers and floats. I'd not do that. You would do that in C, for instance, because you don't have an alternative. C has no clue about references. What you would do in C is you would indeed determine the address of where A is. You would determine the address where B is and implement swap that way with pointers to memory locations. And that would be the C equivalent of this. It's not quite equivalent, but that is something that C would do. You could also just create memory addresses A and B, put values in those memory addresses, and then swap the values of A and B, which are the addresses. And that's what we're referring to. So for numbers or something small, I wouldn't do it. For very large data structures, that can indeed be an option. But we will deal with that later on much more extensively. Because then we need pointers. We need to know what pointers are, and we're not that far yet. Does that more or less answer your question?
Yes, thanks. That's clear.
The main answer is we'll deal with it later in more detail. Okay. So basically, modifications here are in calling and in callee and calling context. So variable name is basically a thing related to memory address. Sort of, yes. It's what you could say is a name for a memory location. So indeed, if you assign the value of y to x, it essentially means that you copy whatever is in the memory location that y points to the memory location that x points to. That is basically the idea. If you view a variable as a name for a memory location, that typically clarifies a few muddier concepts in C++ and in C. It's something that you worry less about in a language like Python or MATLAB, but I find personally that in C and C++, it helps to think about it that way. So that's basically the idea. So the contents of the memory location is overwritten, not the memory location itself. So if I assign, suppose that x and y are both integers, and I assign y to x, it's only about the values. So basically, again, let me make a drawing. Okay, let me clear this thing. Yeah, they changed the user interface and I'm still not used to it. Okay. Yeah. So I've got a variable x. Let's call them integers. Int x, I assign 3. Int y, I assign 5. Let me try and make that a bit more readable. Again, I've got the memory of my computer. So I've got a place in memory where I write 3, and that's what x refers to. I've got another location in memory where I can store the integer 5. That's what y refers to. If I now do the assignment x equals y, the only thing I do is that I override the value which is in this memory location. So I'll just write the value which is in this memory location, copy it to this memory location. So basically this will be 5 as well. So x and y still point to different places in memory, but they happen to contain the same value. So if I now would say, okay, y is 9, then this memory location would be updated with the value 9. That memory location still contains the value 5. That's the idea. Okay? So assignment is a value assignment, not address reshuffling. Okay. All right. We can do memory reshuffling as well. That's dealing with pointers. This we will do later because you need it in C++ anyway. Just call by reference is actually the more convenient way of doing that. And if you can get away with references rather than pointers, then you're typically quite happy. Okay, so one of the things which is also possible in C++ that's not possible, for instance, in MATLAB or in Python, is overloading. So, of course, now I've written a function swap, which allows me to swap two integers. But of course, it might be nice to have a function swap that allows me to swap two floating point values. Very simple. I can define a second function with a different signature. So the name of the function is the same. The return type of the function, in this case, happens to be the same. But what is different is the type of the arguments. So I can have functions with the same name and a different number or a different type of arguments. That's perfectly allowed. And in that case, we call that function overloaded. So the function swap is overloaded for, on the one hand, integer references, and on the other hand, double references. Okay. Of course, I'm still duplicating the code. And now you might look at this and say, well, okay, but this function swap at the left side of the slide and the function swap at the right side of the slide, in fact, do the same thing if I were to substitute int for double. If I just replace everywhere int by double, then the rest of the code is the exact same. And indeed, C++ allows us to do what is called generic programming using templates, which allows us to parameterize the type so that we don't need to write multiple versions of swap. We can do a swap with the same function for integers, for doubles, for characters, even for strings. That would even also work. But that's for later, and that is called generic programming or using templates. Okay, but remember, functions can be overloaded. All right, recursion, easy, nothing out of the ordinary. The function factorial just calls itself as part of the execution. So nothing special. Typically, the compiler will do something reasonably efficient with a function like this, but of course, recursive implementations are typically slower than non-recursive versions, than iterative versions. And every recursive function can be converted into an iterative function. That's always possible. So typically for performance, you will try to avoid recursion if you can. Okay, so our function now is pretty straightforward. Well, our task, remember that's where we were going. We were digressing about functions, but let's go back to our initial tasks, which was to rewrite a file. So we have our function distance, which computes the distance of a point to the origin. Very straightforward. And now we have our main function. So in our main function, we declare two variables of type double. And notice I don't bother to initialize them, because in the next statement, which is a while, I'm going to read from standard input. So standard input is std_cin, and I can use the getFrom operator in order to read from that data stream, from that text stream. And since I'm reading double precision numbers, I'm going to, the C++ compiler is going to generate code that not only reads a sequence of characters from cin, but also converts it into a double precision number. And in this case, I'm reading two doubles, A and B, so basically the X and Y coordinates in my data file. And then I'm writing to std_cout the result. Okay, so let's quickly code that so that I can show you a few things. Transform, whatever, I don't care. Okay, so includes string, includes 0, and 3. No arguments, so I omit argc and argv. Then we have double. Let's go with X and Y in this case, just to make it a little different. While I can read from standard in, and I can read two double, okay, two double values. Okay, I'm going to compute the distance and write it out. I'm going to do that in one go. I'm not going to bother with the function. Yeah, you know how to write a function, so let's not bother. I'm just going to compute x squared, y squared, and new line. Okay. Well, and okay, that's my function. Easy. Now let's also create a small data file. Not a good idea. I always forget whether I have to do a split or a visual split, a vertical split. Then, okay, let's go here and let's create a data file. Okay, so 3, 4, and another point at 0, 5, 5, and another one at -2 and 3, and okay, so that's my data file, and now I can compile my code. So that would be, let's go here again, and let me show the code which I'm actually working on. So that was transform. So, okay, so how do I use it? Well, what I can do, of course, is I can run the file, and then it just sits there waiting for input. So std_cin is going to read from the keyboard. So I can now type numbers, for instance, 3.0, 4.0, and if I hit return, then from cin I can read two floating point values, so double precision values. So x will be 3.0, y will be 4.0. So then the while loop can be executed, and the square root of x squared plus y squared is going to be computed and written to standard output. See, I can type the next pair of numbers, -1 and 0, which should give me 1, etc. If I want to terminate the input, I can do that with Control D. So not Control C, but Control D. Okay, so this would be kind of annoying because I would have to type my values. But of course, if you're familiar with Linux, you know that you can actually use a file as input. You can send data.txt to standard input. And now, of course, I will get 4 values, 1 for each line in my data file. Okay. And of course, this is nice because the only thing I need to know is how to read from standard input, how to write to standard output, and I don't need to explicitly open and close files for this type of very simple things. So the while cin is true as long as you can indeed read. Well, no, not only it is true as long as I can read 2 doubles. So let's do that again. So as you can see, this works, no problem. But now it also ends because it can no longer read from the input stream and convert that to a double precision number. So the ABD is not convertible to a number, so the while loop actually also, well, the condition also evaluates to false, and the while loop ends, and my program ends. So that's what's happened here. So indeed, I can terminate this program in 2 ways, either by typing something that is not convertible to a floating point value, to a double precision value, or by typing Control D. Indeed. Control D just says end of input. That is the convention, the special character to indicate the end of a file. Okay. Actually, I think it's the null character, as a matter of fact, which is the same as you use to end strings in C. But yeah, doesn't really matter. That's under the hood. Okay, so task accomplished. Hooray, hooray. We have a very nice program that can do this kind of thing. Well, almost, because I wanted it to go to a file, and now it goes to the screen. I can easily get it to go to a file by redirecting the output of my application a.out into the file.txt. The base thing. Yeah, the base thing essentially is the Conda environment I'm in. So I'm in no Conda environment now, so that's why there is a base. If I list my environment and go to something, let's say, I don't know, whoa, this is very hard to read. Let's decrease that a little bit, because otherwise I can't even see what I'm doing here. Okay, whatever. So let me increase the size again. And okay, so Mamba activate scientific Python. Accept that. I don't have scientific Python, most likely. Containers. I'm pretty sure I have that one. Then you see that its base turns into the name of the Conda environment I've currently activated. So I'm going to deactivate it because I really, really don't want to be here. And, okay, back to base. So that's what it does. Simple. Also, you will notice, well, not here, but sometimes you will notice that my prompt does very weird things. For instance, it will also show the branch I'm on in the Git repository. Here, I'm not working in the Git repository, so you don't see it. But my prompt really shows a lot of stuff, which is sometimes convenient. All right. So, mission accomplished. We have our data transforming thing, and we even don't have to deal with files from within C++. We just deal with it at the level of bash by using input redirection. So we direct the input into standard input, and we capture standard output, we redirect that to a file. Easy. Okay, so here's the output. All right, so I/O streams, we can do two things with them. We can read from them, and then of course there is only one relevant standard stream, and that is CIN. And basically that's STD CIN, either it's keyboard or I/O redirection. And also you can read from files, which this we'll deal with later. Then we explicitly open a file and read from an open file stream. The operator for that is get from, and writing to. Similar, we can write to standard output. Then we use std cout, that's the screen or I/O redirection. Or we can also write to standard error, and that's cerr. And again, either to screen or I/O redirection. Operator is send to. And of course, we can also open files, write to them, using the same operators, so that's convenient. Okay, so basically that means that if we read from standard input and we read something that will be stored in a double value, in a double variable, then you get automatic conversion from the string which is in standard input, it's just a stream of characters, to a double precision number, and that conversion is automatically. And the opposite is also true, so the result of the dist function is a double precision number, and that is converted to string representation automatically if we use the send to operator. So that's all automatic, so that's convenient. All right, so this is the actual I/O operator semantics. So the semantics of the get from and the the send to operators. I'd say just read it at your leisure. Essentially, I think you understand what it does, but it's useful to have the semantics somewhere written out explicitly. Okay. So the while statement, we already saw the use of the while statement. It's not a surprise because basically in any programming languages, you have something that is equivalent to the while statement. So of course, it's going to be repeated as long as the condition, which is always between round brackets, by the way, is true. So for Python people, you need the round brackets here. The syntax requires this. In Python, you can omit them, but not in C++. You have to have the round brackets. Okay, so this thing will compute the greatest common divisor of two integer numbers. So that's quite straightforward. That's a Boolean condition, so yeah. This means that if you have a while loop, it is executed 0 or more times, because if the condition initially evaluates to false, the while loop is never executed. So basically the if statement which is in there is never evaluated. So a while loop is 0 or more times. Okay, so it's of course a repetition statement. And then we have the do while. So it's an alternative to while, and in my opinion, less frequently used. So we start with do, then you have the body of the loop, and then we have the while. So the condition is only evaluated after the body has been executed. So the difference with while is that the do while is executed at least once. So after the first execution, the condition is evaluated. If it evaluates to true, the do while will be evaluated a second time, or a third time, or a fourth time. As soon as the condition is false, it stops. So it's at least once. So that's the important difference. Okay, the if statement is again what you would expect. So if something else, something else. So no surprises there. In principle, you can leave out the curly brackets here because there's only a single statement in the body of the if and in the else. I would recommend you don't, because a very easy mistake to make, especially for people coming from a Python background, is the following. Let me just do this. Let's say int a is true. If a is less than 1, then I do something. Else okay, so I don't need to explain you what's going to happen. You know this. So basically, this will just print this happens. Let's see. No surprise. But now I change my mind and I want something else to happen. So I recompile, execute it. Oh, yes, it happens. But yeah, fine, because indeed we are in the else, so both things should be executed. Okay, no problem. Now, let's make this -1, -1. Let's recompile and let's execute. And this should not happen. Because now, of course, what we expect from the layout of the code and what was kind of our intention is that the statement on line 9 should be part of the else. However, the condition evaluates to true, so line 6 is executed, and still line 9 is executed. Why? Because the way that the C compiler, C++ compiler interprets this is in fact that this statement is executed after the if-else. So this is the semantics now given visually. So it's very easy to make this kind of mistake, especially for Python programmers. So I would advise you to always use curly brackets, because then you're really, really sure what is part of your else and your if and what not. Now the behavior is as expected. So basically now I only get the output generated by line 6, and obviously not the one by line 9, because that is the else part. Now it's very clear and you don't make a mistake. So I would suggest to always use curly brackets, even if you, according to the syntax, can omit them. In most circumstances, not always, but in most circumstances, I'd really recommend to do this. Okay, so basically, yeah, this is all straightforward, nothing special here. And of course, you can leave out the else part of an if statement. That's pretty obvious. And you can also chain things. You can chain if statements. So this is also a little different from Python. In Python, you would have elif, which here in this case you don't. Here you have else space if. That's the only difference. And again, if you use curly brackets here, it's very clear what the else belongs to. because if you leave out the curly brackets, there may be some doubt about it. Well, there is no doubt about it. The compiler exactly knows the semantics, but you might not know the semantics. And then you have to have a look at the specification, what the last else, which if statement the last else belongs to, if you don't have curly brackets, and it's a bit muddy. So I would recommend using the curly brackets. Okay, so this is of course a conditional statement. Python has C++ has one more conditional statement, which is the switch statement, but I'll come back to that later. There is also a form of the if statement that is only valid in C++ 17 and above. It's not in the slides yet. Let me perhaps give you an example of that. What you typically want to do is to limit the scope of variables as much as possible. And one of the things you need to do if you have an if statement is, and you need a local variable there, is you can't, typically. So what you typically would do is, yeah, I don't have a good example. Let me do this later, because I know that I have a nice example somewhere, and now I have to invent something, and I'm not sure that I can get a nice one on the fly. So let me do it later, but I'll return to it later when I discuss some differences between C++ 14 and C++ 17, new features of C++ 17. Okay, so the last statement I'd like to discuss now is the for statement. So that's also a repetition statement. And of course, you were quite familiar with that in Python. But in C++, we actually have two for statements. So this is the old style for statement. And it consists of 4 parts. So the for statement in the round brackets has 3 parts. The first part is initialization. So I can declare a variable I, which is the variable of my loop, and its scope will just be the for loop, nothing more. And its initial value is 2. Then I keep on doing my loop as long as I is less than or equal to n. Okay, so first step, I set I to 2. Second step, I check whether I is less than or equal to n. Let's assume that's true. Okay, then I'll execute the body of the for loop. So in this case, I'll assign a new value to the variable val. Okay, then I'll increment the value of I by 1. Okay, so I now has the value 3. I check whether I is less than or equal to n. If that's the case, again, I update the value of val, and I increment I by 1. So I is going to be 4. So let's assume that n was equal to 3. So I check the condition. Condition evaluates to false. I do the next statement. So in this case, I return the value of val. And this, of course, implements the factorial function. Okay, so these are the parts of the for statement: initialization, condition, body of the loop, and the update of the loop variable. So that's the canonical form of a for loop. You can leave out any of these parts except for the body. That's basically your typical for loop. There is another for loop, the range for, but this we'll deal with later because we can't really show it now. What's the difference between plus plus I or I plus plus here in this case? In this particular case, nothing. I would be free to use either plus plus I or I plus plus. And typically, if you look at example code, you will very often see I++ rather than ++I. If you look at C code, you will always see I++, never ++I in this context. However, C++ is a little more sophisticated, and you can do this type of for loops not with an integer index, but with iterators. We'll see that later. And then there is a difference between ++I and I++. ++I is more efficient if I is an iterator. And that's why I make it a habit to write ++I in this context, because then I won't forget to do it when I'm dealing with iterators rather than simple integer loop variables. So that's why I do ++I here. But in this case, it makes zero, absolutely no difference at all, because this is a stupid integer, and whether I do ++I or I++, exact same thing, exact same performance. However, if I were an iterator, then things are different. Then you better do ++I, because I++ would be slower. Okay. So basically initialization, Boolean condition, the loop, and then of course index change. And you evaluate again the condition, you do the loop, you do the index change, and so on. So that's basically the semantics of your standard for loop. This is in many circumstances old style, and we will see an alternative, but this is only useful when you know about data structures, so that's for later. Okay, so of course for loop, the body is executed 0 or more times, so that's the same as for the while loop. Of course, you can write any for loop, classic for loop, as a while loop, and actually also range fors you can write as while loops, and also vice versa. So in C++, you can actually rewrite a while loop in the form of a for loop. That is entirely possible. Okay, so you're familiar with break and continue and that kind of thing. So earlier in the comments you have mentioned that don't use end line. Yes, too much. Yeah, indeed. Yeah. Okay. I can tell you now. So basically, suppose I'm doing something like this. Okay, I have something here. Well, I'm just going to use this one. Okay, so what I'm doing is, let's say for, I'm going to do something simple. Int I is 0, I is, let's make that a rather large number. That's a billion. And I need ++I. And what I want to do is std cout. Write I and okay, so and end of program. Okay. All right. Let's compile this. And for good measure, let's optimize it. So I use -O2 to do optimization. And this was CPP. I will rename this file later because this is stupid. But anyway, output is new line. Okay. All right, let's make a second version of this. So G++-O2 CPP, and this is endline.exe. Okay. All right. So let's time this. And frankly, I don't know. I've never tried it. So let's see what the difference is. I'm going to run a new line, and I'm going to redirect the output to remove.txt. This will take a while because I'm writing a billion an integer. Well, I'm writing a billion integers to a file, so this will take a while. I hope it's not too long because otherwise I have to recompile it. But it should be something like 30 seconds, I guess. By the way, this allows me to, while we wait, talk a little bit about a feature which I'm using here. So just like in Python, I can actually use separators for numbers. And basically this makes it easier to read because now I see immediately that this is 1 billion. If I just type a 1 followed by 9 zeros, I have to start counting. And of course, it would be the same thing, but this is much easier to read. So in Python, you would accomplish the same thing using underscores. So that's just something that's useful to know. You can also do this for floating point numbers, by the way, just like in Python. And frankly, I don't know in which version of C++ this was introduced. Okay, so it took 1 minute 12 seconds. So let's do the same thing with end line. Okay, and let's come back to it because it's a bit silly to sit here and wait for quite a while. So let's just go back here and let's see the results later. Okay, so break and continue. Break is very simple. If you have any repetition statements, whether it's a while, a do while, or a for, and you have a break, that stops the iterations, all of them. While loop, for loop is done. So basically in Fortran, that would be exit. In Python and C and, okay, in MATLAB, I don't know actually. But there it would also be break. So there are no surprises here. Continue, you're also familiar with, because again, that's the same thing as in Python and C. For Fortran, that would be cycle. But it's the same thing. So basically, the continue here will skip the rest of this particular iteration when the line starts with an hash character. It will not do the conversion of the line to a string, from a string to a floating point and add it to sum. It's just going to skip to the next line in the input. So continue just skips the particular the rest of the particular iteration and continues with the iteration, either with the while or the for loop. So no surprises here. This is all pretty well known. Just for the record, so here I'm reading from stdcin, and I'm using the getLine function for that. So this reads a line at a time. And as soon as cin has been exhausted, then of course getLine will return false, and this stops. The while loop stops. And I'm using a string, an std string, to store the line in. And you can see that I can convert a string to a floating point value using the std s2f function. If I want to convert to an integer, it's s2i, s2 integer, string to integer. Okay, so this thing is still busy, but these are your break and continue, nothing special. Then blocks. So we have used a lot of blocks. Anything between curly brackets is in fact a block. But you can also just insert a block somewhere in code, regardless of not attached to some statement. So in this particular case, we have a block here from this line Oh, wait, where's my, from this line to this line, that's a block. Okay, so why do I emphasize blocks? Because blocks determine scope. Scope is where in the code your variable is defined. So let's start at the top of this code fragment, and we define a variable, I, and we initialize it to 3. Okay, so the scope of a variable is from the point it's declared up to the end of the block it is declared in. Okay, so we're assuming that somewhere here is a block, for instance, the body of our main function, whatever. So we have int I, in this case would be in scope for the rest of this code fragment, from the beginning up to the end. Okay, so of course, when we do cout here, the value 3 will be outputted, no problem. But then we start a new block, curly brackets, and we again do cout of the value of I. Okay, no problem. This I is still the I which is declared here outside of the block. But now inside of the block, we declare a new variable I and assign 5 to it. But this I is declared within the block. So it overshadows the I which is declared here. So this is a local version of I, a variable with a distinct variable referring to a different memory location. So this I in outer scope, the original one, will point to a memory location where there is the value 3. The I at this line here will refer to a memory location where the value 5 is written. So if I now in the next statement do cout of std cout of I, it's going to output 5. Okay. So as I mentioned, the scope of a variable extends from the point it's declared down to the end of the block it's declared in. So this version of I, which has the value 5, its scope only extends to the curly bracket here. So if I now do cout I, this is again the I which was declared in the first line. And we get 3. So now I have a for loop where again I use a variable I. But notice it's a declaration here. There is type int I. So this I is again local, but it's local to the loop. So in this loop, it will start with the value 7, and it will end when I has the value 10. Okay, so what's going to be printed is of course 7, 8, and 9. Then I will have the value 10. I is no longer less than 10. So the for loop ends. So then the question is, the last output statement, cout I, what's that going to refer to? Well, it's going to refer to the I which was declared at the beginning of this block. Because the scope of this I in the for loop, so the iteration I, is in fact just the body of that for loop. So that is only valid within the false statement and of course what it's going to execute. So this is going to output 7, 8, and 9, and that is again going to output 3. Don't do this. I mean, don't overshadow variables, because this is very confusing and it's an utterly bad idea, but you can do it. So you can also do it by accident, and there is a compiler flag to warn you about it. And it's a good idea to actually activate that. I think it's activated by W extra, and then you get feedback that what you're doing is maybe not a good idea. Because this can have, if you do it accidentally, it can have very weird consequences and create bugs which are non-trivial to find. So that is, well, kind of important. And I have to, again, fix this slide a little bit. So that's the block slide, which I need to adapt. Okay. Is this more or less clear? So variable scoping is important. It goes from where the variable is declared up to the end of the block in which it is declared. That's the idea. Okay. So C++ supports C-style arrays. Well, it's not good. I mean, we have alternatives in C++, but still it's useful to know about. So if I want to declare an array with 5 elements, each element has type double. I can do it in this way. So this is my array declaration. So I get memory space. It will be contiguous data storage in memory. So first number, second number, third number, all one after another in memory. And it will be fixed size. So if I declare an array of 5 elements, that array will have 5 elements up to the end of its scope. It's never going to change size. Also, it will have always values with the same type. So it's very different from a list in Python, for instance, which can have any value as elements and which can have less elements or more elements depending on whether you append values or you delete values. Okay, so values are of course not initialized here, but I can address values in the normal way. You need the you use the square bracket operator to index arrays, and indexing starts at 0. So that's important to realize. Okay, if you want to pass arrays to a function, the problem is that in that function you have no way to determine the size of the array. So with classic style C arrays, you always need to pass the size of the array as an additional argument. This is on the one hand ugly, on the other hand it's also error prone. So that's why I really dislike C style arrays, especially since we have nice alternatives in C. But nevertheless, it's useful that you know about them, because you will see a lot of code that actually uses C-style arrays, although probably it shouldn't. Or you may use C-style arrays if you know what you're doing and you're designing your own data structures, then C-type arrays are still quite useful. But then, of course, you know what you're doing, and then you make sure that you don't make mistakes. Okay, so basically this is a bit of a view of what's going on in memory. And remember, zero-based indexing, so that's for the MATLAB and the Fortran people. Okay, so there are typically quite some alternatives in the standard template library. For instance, std vector, for instance, std array, or std vol array. Actually, there are at least 3 alternatives for arrays, C-style arrays in C++. Okay, let's have a look whether the I/O thing is done. So yes, no, it's still not. So I think we agree that the performance difference is pretty enormous, because this was 1 minute and 12 seconds. Meanwhile, I've explained like 3 or 4 slides. So that's definitely a lot more than 1 minute. Maybe it will end before the end of the training session. Let's keep it running. It doesn't matter. Okay. So const. If I don't want the value of a variable to change, then I can put const in front of the declaration. So n now cannot be modified. It will always have the value 10. Of course, if I declare a variable const, I also have to initialize it. That is syntactically required, I think. And anyway, it wouldn't make sense otherwise. So basically, if I were to try to assign a different value to n here, for instance, the compiler will complain. It will tell me, hey, wait, you can't do that because in fact, this is a const and you're trying to assign to it, so you're trying to change the value. Now you can't do that. So this is one use of const. The other use of const is in function arguments. This is also pretty important. So here I'm saying that I can't change the elements of my array. So here I should get a compilation error as well. This will give me a compile error, and that will also give me a compile error. A constant from a text file. Yeah, you can read the text file. And yeah, okay, I see what you mean. Yes, I can, because what I can do is I can read the value from the text file and then assign it to a variable which I have declared const. So yes, I can do that. Okay. So basically, what we have done is more or less covering all the features of C++ that it inherited from C, with a few exceptions. So basically, I've talked about overloading. Can't do that in C. I've talked about call by reference versus call by value. You can only simulate that in C, but apart from that, most of what we've seen is very much like C. IO stream is also, of course, something typical for C++, but this was mostly C. So things get interesting when we talk about user-defined types, because there we can do more interesting things. Okay, my fan is spinning down, so perhaps, no, it's still not done. Okay. So we have 40 minutes left. Let's start on user-defined types. So basically, let's revisit the data types in a bit more detail than we did before. So for integers, actually, we have a number of types of, now it's really spinning down. Would it be done? Yes, it's done. Okay, so difference, 1 minute 12 seconds for \n, 15 minutes, almost 16 minutes for end line. Okay, why the heck? Well, what I told you is true, but incomplete. So what stand std end line does is indeed, depending on whether you're running on a Windows computer or on a Mac or Linux system, it will either generate just an end of line, well, just a carriage return line feed, or an end of line. Okay, but that can't be it. So that can't explain the difference. So there is another thing that std end line does. Okay, how does I/O work? Let's take a step back. If there is something that is really, really slow compared to making computations, such as additions, divisions, square roots, whatever, then it's writing stuff to a file or writing stuff to the screen. This is really, really slow in comparison. Okay, so I/O operations are kind of expensive. If you have an application and it wants to write something to a file or something to the screen, which is basically the same thing, then it actually asks the operating system to do that. So the application itself is not writing something to the screen or something to a file. The operating system is doing that. Okay. Now, of course, people who develop operating systems know that writing stuff to a file is slow. So they want to speed it up. One way to speed that up is, rather than for each individual request to write something to a file, immediately do that, what the operating system will do is write it in a buffer. And if the buffer is large enough, if the content of the buffer is large enough, then write it to the file. So it will aggregate many small write operations into one write operation of a lot of data. That's what it tries to do. And the reason for doing that is that an individual write of a lot of data is a lot smaller than a lot of writes of small parts of that data. That's how things work. So that's what the operating system does. Okay, however, if I use SDEndLine, then the code, well, application is also requesting the operating system not to do the buffering, but rather to write whatever immediately to a file. Okay, but that means the operating system can ignore that. It's free to do that, but typically it will actually do what you ask. So that means that it will do all these individual small writes. And you can see what the overhead of that is. In this case, it's a factor of 14 or 13, whatever. An order of magnitude slower. So basically here, in this context, an end line is a really, really, really bad idea with respect to performance. However, end line is still quite useful because sometimes I want this to happen. I want to flush. So the technical term for this is a flush. If you're familiar with C, you will know that there is a function fFlush, which will actually accomplish the same thing. It also tells the operating system, please, anything I've written up to this point, please write it now to the file. I'm asking you politely to do this, please do so. And the SDEndLine in C++ is doing such a flush under the hood. So that's why it's enormously much slower if you have many small writes. Okay? All right. So, data types. Actually, I mentioned int, but there is another integer data type, and that's a long. Now, the C++ standard doesn't say anything about the sizes of int and long. It only says that int is larger or equal to a character, so it has more bytes or the same number of bytes as a character, and that an integer has less than or equal the number of bytes of long. That's all the C++ standard says. In practice, with any compiler I know on any system I ever worked on, an int is 4 byte and the long is 8 byte. But you can't really rely on that because the standard doesn't tell you so. It's just usually the case. So if you really, really care whether you use 4 bytes or 8 bytes, you should use a different data type. Okay, so for each of them you have an unsigned variant. So this is an unsigned integer. So if indeed our int is 4 bytes, then an integer value is minus 2 to the power 31 up to 2 to the power 31 minus 1. An unsigned integer would go from 0 up to 2 to the power 32 minus 1. Similar for long, but substitute 64 for 32. Okay, so if you really want to make sure that you get the right size of integer, you can use these types here. So basically here we have an int8 underscore t. So that means it's an 8 bit integer. Okay, 8 bits means that you can store numbers from minus 128 up to 127. You also have an unsigned int8, and that would go from 0 up to 255. Then you have 16-bit integers, so that's basically from minus 32,000 to 32,000, or from 0 to 65,000, in 32 and in 64. That's basically the idea. You also have size t, which we will use occasionally, and that is typically the same as a uint 64t. But we'll talk about size t later. Okay, so if you want to use these, then you have to include cstdint. Then you have access to those types. Okay, so for real numbers, already mentioned, float and double. Vectors and matrices, we have a lot of choice. Either you can use C arrays directly, please don't. There are a number of array implementations with different properties in the standard template library. So one is std array, the other is std vol array and std vector. We'll talk about them in more detail later on. So of course, which data type you choose depends on the problem you're trying to solve. Choose it as close as possible to what you're doing mathematically. So if you're talking about real numbers, use float or double. If you're talking about integers, use an integer, etc., etc. Okay. So defining structures. If you want to represent tuples, you can do that using a struct. So we create a new type. The name of the type is particle, and it's a struct. It has a number of fields, or attributes if you want, or members. Basically, in this case, it has 5 members. 3 of them are of type double, x, y, and z. The 4th is also double, that's mass. And then we have a 3rd one, which is an integer, and which is the charge. So this is sort of like a tuple in Python, except that you can reassign values of members in a struct. So that's entirely possible. Okay, and for each member, you also have to indicate the type. Okay, and members can have distinct types, no problem. So how do we use them? Well, we have declared our struct particle, so now we can say, okay, particle P1 and particle P2. And we can assign the different members directly, again, using the universal initializer. So this would be X, that would be mass, that would be charge. And of course, you would have to add the values for Y and Z also, and Z also. Okay. If you just define particle P1, then of course, nobody knows what the values of X, Y, mass, and charge will be. Okay. Using such variables, so for instance, to P1, the X member, I can assign -2.0. Or I can access the mass with the dot notation. So this looks like named tuples in Python, but again, the distinction is I can happily assign to structure members. That's no problem. Why is there a comma after X and not after mass? Yeah, that is a typo. There should be a comma here after the 0.5. There should be a comma. It's just a typo. Thanks. I have to correct that. Struct. Yeah. Okay. Then, how do you pass structures to functions? Well, remember, by default, we have pass by reference. Pass by value. So if we do just pass by value, then in fact we will create copies of these structs. And now it's not just a single character, it's actually quite some data which needs to be copied. So typically we want to avoid that, and we can easily avoid that by passing a reference to the function. So we declare our function distance, which takes 2 particles, and will compute the distance between those particles. But they are going to be passed by reference. So no copy is made. But of course, if I pass by reference I can in fact modify P1 and P2. But if I want to compute the distance, I don't need to modify my particles. But if this is a sophisticated function, I could do this by accident. So if you want to pass arguments into a function by reference, but you only want to do that for performance reasons, not to modify them, then of course it's good practice to make those arguments const. Because now if I accidentally would try to modify P1x, for instance, then the compiler would complain. It would say, nah, you cannot modify anything in P1 because you set it const. Now you're trying to modify it. I don't think so. So basically, if you pass references for performance reasons, always use const. And that's the bottom line here. Okay. So here's another example where we actually do want to modify our particle because this function move, as you can see, it doesn't return anything. So that means it has to have side effects on the arguments we pass in. So again, we want to modify P in this case, so we pass by reference. But now, of course, we don't use const because we really want to change it. And then we have dx, dy, and dz. And those are displacements in the x, y, and z direction. And we update px, py, and pz, respectively. Okay. So it's important to make the distinction between passing by value, which we're not doing here, because we would copy our data structure. And we want to avoid that in the first example for performance reasons. So we pass by reference, but then we use const. Here we want to modify the particle, so we have to pass by reference anyway. And we don't use const because we want to change the particle. Okay? All right. So, structures versus classes. In fact, and that's something that even many C++ programmers don't really realize, structure and classes are in fact the same thing. Almost. There's one distinction. So basically, structures and classes are very useful because on the one hand, they're easy to use and it's easy to declare them. And of course, they make sure that you can create your own data structures, your own representations of your data. For instance, I can create something that represents particles, or I can represent something that represents a vector field or whatever. So that makes it easy to use and easy to reason about. So they're good to do modeling your physical system or your theoretical framework into this kind of data structures, which you can define for yourself. So in structures, members and methods are public by default. So I can access anything if I don't specify restrictions. And that's the idea. So the disadvantage of that is if you can modify members inadvertently. For classes, it's the other way around. Members and methods are private by default. So you need to specify inspectors, for instance, or mutators in order to view values, get values, or change values of your class members. Let me show what I mean by that. Okay, I'm going to do IO, so I don't care. I will create a struct. Let's call it point, and it's going to have 3 members, x, y, and z. Well, let's make it x and y, point and 2D, and that's it. That's good enough. Okay. So I'll also create a class. Make a distinction. I'll call this point struct. But of course, these things are identical, except for that one is class and the other is a struct. Okay, now I've got my main function. This, and now I create a point. So I have a point struct PS, and I initialize it to 3.0 or 4.0. Universal initialization, no problem. I do the same thing for my last point. Let's go with PC. I initialize it to the same thing. I really don't care. So what I can do now is say that PS x is equal to 90.3. Okay, something is wrong here. What did I do? Go to point class. Huh? Why? Ah, yes, I don't have an explicit constructor, and I can't even do this because, in fact, my attributes are private. So I can't do this. Even initializing it in this way is not possible with a class. Why? Because I can't access x and y, and hence this initialization is not even going to work. So if I leave it out for a second, just to show you, this will work. I can perfectly initialize struct in this way, and I can assign things to its members. I can also use it, so I could do std cout yes.y. That would also work. Okay, it doesn't work with class. With class, I'd actually have to define constructor. So basically a function that allows me to create point. So I could do x value to y value. We'll come back to this in more detail later on. And I'm going to make this really, really simple here in this case. I'm just going to do it in a way I would normally not do, but just for the sake of the argument. I can assign x value to x and y to y value. Okay, all right. And now I'm allowed to do this. Yeah, not really. What did I do now? Point class, int is private. Ah, yes, of course. Yeah, stupid. Everything is okay. I'm telling you that everything is private by default. I have my constructor. I don't say anything, so of course it is. So let's make that public. Okay. All right. And now still something is wrong. What am I doing now? Narrowing conversion. Yeah, this is stupid, of course. Complete idiot. Why do I make this int? If I actually double. Now it's almost happy. There's something wrong here. Ah, yes, of course, I did not include. Oh. Now it will compile. So now this is okay. See, but I have to create an explicit constructor, so a function to actually, it is similar but not quite the same as init. So it serves the same purpose as init, but Dunder init in Python is not a constructor. So the constructor in C++ really makes the new object, while the Dunder init initializes an object, a new object, that the Python runtime has already created. So that's a slight distinction, but semantically it's more or less, it serves the same purpose. So it serves the purpose of initializing a new object. That's for Dunder. And for C++, it will also do that, but it will also do the actual construction. So it's a little different, but it's similar in spirit at least. Notice also for the Python people, I don't need to mess with self. So C++ knows that if I access X here, then I actually mean the X in this object because it's declared here. So I don't need to mess with self. If I want to, I could write this. So that's going, no, it's not going to work. What do I need to do? Request for number X pointer class. Okay, yeah, I need to make this a pointer, of course. Yeah. All right. So basically, yeah, I didn't want to go into this, but anyway, so I can use this pointer if I want to, but typically I don't need, and I don't want to do this. So normally I try this. Okay. So what still doesn't work is this. See, compiler is unhappy again. I cannot access this X because it's private. Okay, so we'll deal with this later. What I would have to do is write a setter method, which is, you also know the concept from Python. You have these properties. And so basically what I would have to do is define a setter in this case in order to set the value, or to access the value, just to read it, I would have to create a getter. I'm not going to do that now, but just to show you the difference between a struct and a class. Apart from that, it's the same thing. I could make this struct behave the exact same way. If I were to put private here, same behavior. So now it's not going to compile anymore. And here, note candidate point struct. Yeah, now it's going to be very unhappy because indeed I get that same error here. It says, well, okay, you can't do that. So now I would also have to add a constructor and so on. But it's just a matter of the default being different. That's all. Apart from that, in fact, it's all the same thing. A class and a struct are the same. So should you use one or the other? Well, what I notice in, let's say, older C++ code is that people prefer class, while now they're moving much more towards struct. So if they want to use a class, so if they want private members, they typically tend now to use a struct and to hide the members using private. But that's a bit of a shift in style. What's the use of something that's private? I don't want you to play with it. It's my object, it's my members, you should not play with it. No, basically it's to hide state. We will see some interesting examples later on. So I would suggest to defer that answer to when we really deal with object-oriented programming, because then I have some nice examples, and otherwise I'm just skipping ahead to something that I'm going to explain anyway. So let's perhaps just postpone the answer up to the point where this is dealt with. It might even be in this section. I don't quite recall. So class attributes can be private. They're private by default. I typically put it private anyway, so that I'm really making clear what is private and what is public. So that means they can only be accessed, read and write from within the class itself. Okay. Just to give you an example why I might want to do this, perhaps. Suppose, typically in a simulation, I would not do this, but suppose this were a business application. And suppose that one of the attributes is price. What I don't want under any circumstance is that the price of an article in my shop is negative. So I don't want that just anyone who is using an article in an object of the article class which represents my shop is able to put a negative number as a price. I really want to avoid that because then I'm losing money. Okay, so in that case, I would create a class article where my price is private and where I define a method to set the price, but I'll check whether the value I pass in is positive. If the value is negative, then I generate an error. So that's one reason why I would make a member of a class or a struct private, because I don't want you to make mistakes. That's the idea. There are some other reasons as well, but we'll see some more examples later on. But that's the upshot. So members can be private, can be public, and they attributes in general determine the state of an object. So if you think in terms of physics and you think in terms of particles, then what's the state of your particle? The state of your particle is going to be its position and it's going to be its velocity. That's what's determining the state of a particle at some given point in time. Classical mechanics, blah, blah, blah. And perhaps its mass, which would be constant in classical mechanics, but anyway. So that is determining the state of your object. That's the purpose of class attributes. Okay. Then class methods can be public, can be private, depending. And those actually serve to do things with your object. So here is an example. So the double X is actually going to return the value of the X attribute. So of the X position of this particular particle. So it's just a function in a way. A method is in a way just a function. Its name is X. It doesn't take any arguments and it will return a double value. Okay. The implementation is here. So it will just return the X underscore member of our class. So let me go back here. So I defined my attributes with a underscore appended to them. This is something different from Python, where it is, well, it's also a convention to do this, but the reason is different in C++. I'll show you in a minute why this is useful. So the one thing which is a bit weird is this const here. And that actually means that my method is not going to modify the particle, which is true because I'm only returning one of its attributes. So putting const here is a good idea because that tells the compiler, okay, this method call is never ever going to modify my my particle. That has two consequences. If you inadvertently try to modify the particle in the body of the function, compiler is going to complain. So that's one benefit. The other benefit is also that it can do more optimizations if it knows that this is const. So it also has a performance impact. So the mass function is similar, but for the attribute underscore, mass underscore. And then we have move, and that takes 3 double arguments, and it will do the move as before. Note that there's a difference here. So these functions, x and mass, have their definition here in this file, while for move we only have a declaration. There is just a semicolon here, no curly bracket implementation. Okay, so definition for an inspector for x underscore and that is the declaration of a mutator for x underscore y underscore z underscore. So an inspector just shows you a value. A mutator allows you to change attributes in an object. Okay, so this is called on an instance, and methods can be private. Okay, the constructor, I already showed you one. This is a better example. So the constructor always has the same name as the class. So the class name is particle, constructor name is particle. A constructor is a function. It takes arguments. In this case, it takes 5 arguments: x, y, z, mass, and charge. And all of them are double precision numbers except for the charge, which is integer. Okay. Then we use class initialization. So there is a colon here. And then I specify that x underscore, so the x underscore attribute of particle, is going to be initialized to the value x passed as an argument to the constructor. Similar for y underscore and y, z underscore and z, and so on. And at the end of the day, this would be what the constructor is supposed to do. But since it's pretty trivial and only sets some values here, the body of my constructor can just be empty. So this is my constructor. I use that in order to create new particles. So I could do the same thing for my point. I could use this notation. So x value, y value, semicolon at the end of this, and oops, that's too much, and then that compiles as well, and it's the same thing. Let me remove the offending thing here. So this is the default form, or the standard form of a constructor in C++. I can create an accessor. So for instance, double x, and this is actually why we have the underscore thing. So cons x. As you can see, this is not going to compile. Why? Because my function name is the same as the attribute. That's general. Underscores names of the attributes. And of course, I do the same thing for y. And now I can happily do something like this here. Oh, no, it does not. What's going on? Yes, sorry, this I can't do. What I can do is svc out ec.y, for instance. This I can happily do. Oh, can't. Why? Yes, because this is a function. Oh. Okay, if I want to change the value of x, I can also do that. Make that void. The function name is x, and it takes an argument, a double x value, and simply sets x underscore to x. And now, if I do the same thing now, I can do and then I have a setter. So this is typically what you do in C++. So the property thing, which you can do in Python, unfortunately you can't do in C++. That does not work. So if you want a setter or a getter, it's always going to be a function with with round brackets. You can't just use add property or something like that. That unfortunately does not exist. Okay. So all of this is trivial attribute initialization. If you have simple classes, this is a nice way of doing that. You can also do it the classical way, as I showed before, that within the curly brackets you do the assignments. That's also possible. But this is more modern, more preferred style. Okay. So this will create a new instance and initialize the member functions, the members of that particular object. And a constructor can actually be private, which is something you might want to do for factories. Perhaps we will see an example of a factory, but that is why you would do that. Okay, so what kind of methods can you have? But maybe it might be better to postpone that discussion till tomorrow because it's 1 o'clock. And this is a bit too much to do now. So we're not going to do that. So we'll return to methods tomorrow and actually object-oriented programming. Okay, are there any questions at this point? So this we will return to tomorrow anyway. So if this was a bit too fast, we'll repeat it again tomorrow. Okay, if no questions, I wish you a pleasant remainder of the day, and I'll see you tomorrow again at 9. You can use the same link as today, so that's no problem. All right, so see you tomorrow.